All right. Good evening, folks. Day 2 of the Not Ranty show. I'm your host, Brandon Toy. Hope everybody's doing good out there. Thanks for checking in. Let's see who we've got in the chat to start this evening. Got some stuff planned for you. I'm going to talk a little bit more about what we talked about last night with perspective. Got quite a bit of feedback from the ballers in Discord and other places regarding what we talked about last night. So we'll spend a little time on that. Got a couple people in Discord already. We'll see what they bring to the table. And who knows where it goes. Maybe we'll get a baller that'll pop in and, grace us with their presence tonight. That'd be all right. All right. Who do we got in the chat tonight? I am going to start from the top. Got Matrix Media. What's up, man? Rune Thornson, Enigma, Ben Grizzly Adams, The Plain Truth, who says, shout out to Eddie Van Halen. Yeah, very sad news. Eddie Van Halen died today. 65 years old. Ian Matterson, Ian Adams, SE Montreal, Brandon C. What's up, Brandon? SE Montreal, I get shout out twice. Anthony Burrows. We've got, let's see who, Seek and Find. We have Dr. John D. Hey, Dr. John. Balanced Truths, Mark Collard, Crow XE. What's up, Crow? John Sudlik. Sorry if I butchered that. If I missed you, I apologize. And let's go and check on what we got on the big screen here. This is the little... actually, let me bring the guys in from Discord real quick. We've got a couple people in there, and it'll be easier to do that. Hey, can you guys hear me there in Discord? Got Jimbo and Bob. How you guys doing tonight? Cool. All right. Cool, Jimbo. So I wanted to talk a little bit more about the perspective diagram that I have on screen right now that I showed last night. We got a lot of feedback from Dr. Phil Bell, WS, and I think there was a couple other people who commented on this in the Discord and told me how wrong I was. So if you guys remember this is pretty much the prototypical baller debunk that says flat Earth is falsified because of this one diagram here. And the argument is coming down now to, well, it does show perspective. So my contention is that this doesn't take perspective into account. And the reason I say that is because you've got this line here, which represents 5,000 kilometer high Polaris, which is just, this is just theoretical. This is just a number that somebody came up with. But you've got this 5,000 kilometer line Polaris. So let's say you're standing right under it. You're seeing this 5,000 kilometer line, you're looking up 90 degrees. Then you move back 690 miles. You look up at the line. It still hasn't changed, right? Still the same size line on the piece of paper because this is a 2D representation. The angle has decreased to 78.2, but this line remains unchanged. And as you continue to move back, you're still looking at the same line in this diagram. The line never changed. So this is just a 2D representation, kind of a side view. But in reality, what we see is this line gets smaller and smaller as we get further and further. The way they have this drawn here, let's say you went, 1,000 more units, right? You would still be looking up at this line. You are never going to see this line fall down to the 90 degrees. And I say that in itself falsifies this as matching reality. Because in reality, you will get to the point where that will be at 90 degrees, or you won't even see it because it'll blend into the horizon. Would you guys agree with that statement, or you got any other thoughts? No, nothing? Well, according to this diagram, this is the baller's diagram. Remember, this is not mine. Their claim is that this represents reality. And they say, well, you're here at the equator. It's still 26.7 degrees. So obviously Polaris wouldn't work on a flat Earth because when I drew this line to this 5,000 kilometer high, height for Polaris, it's only at 26.7. And in reality, you need 0, theoretically, even though from 15 degrees and below, we don't have good measurements. Oh. Okay.
It on YouTube.
Ah, there we go. Sorry about that, guys. Randy just informed me that nobody's been hearing Bob or Jimbo, so rookie mistake. I apologize for that. Luckily, I was talking quite a bit, but okay. So, Jimbo, can you repeat what you just said, please?
Okay, now this debunk, it has a problem because it's depicting in the values along the line at the bottom, okay, the degrees in arc radians. Okay, now the first one, say you come straight down from the 5,000 kilometers to 90. The next one over is what, 78.2 degrees. There's a difference, but there's no arc. There's no radian to be measured. The radian would have to be measured between the first 2 points, or these lines, these rays that are coming off the 5,000 kilometer point. So from the 90 to the 78.2, you'd have to draw a little arc from point A to point B.
Yeah, I'm not sure I'm following you on the arc there.
Well, 90 degrees, what is that? 90 degrees of a circle, right?
Right. Yeah, this is, it's based on,
Where do you see an arc? Where are you seeing an arc?
Yeah, no, you're not seeing an arc.
This is a misuse of the arc radians, because the arc radians are between 2 points at a time, which would be between the 5,000 miles and 90 and 5,000 miles and the 78.2. You see, you're measuring the distance between those lines at the end point. The distance of the arc that they're radiating out from.
Okay. All right. Yeah, I get what you're saying.
It's a cheat and a deception here.
Well, I agree that it's a cheat and a deception, and I think the sleight of hand is that you're measuring all to the same point, when in reality, when you move backwards, this line gets smaller within your field of vision.
Well, there's something else. I think I want to make sure I understand. This is their picture that you're showing. Is that accurate?
Yeah, this is their concept. Yeah.
This is what they suppose. Okay. So, and what they're saying is it's a problem because the object doesn't remain consistent in reality, and so it can't be this. Is that what they're saying?
Yeah, they're saying that this can't happen on a flat Earth, essentially.
Well, there's another thing that's
wait, hold on. They're saying that this picture can't happen.
Well, I mean, this is what would happen on a flat Earth, and reality doesn't match this.
And in reality, the object does move, right?
In reality, yeah, the object goes down, further down.
Right. Yeah. See, that's the problem. What they've done is they've taken their idea of what the star is and how it works, okay, and they've applied it to a 2D image that they've created, right? Or a 2D concept here. In this image, it's a static image, right? It doesn't change. It's not dynamic. What they haven't included in this, obviously, is the fact that the star does move. The stars move.
It descends as you move away from 90 degrees underneath it towards, well, the 26.7. It's coming down. Here, it's static. 5,000 visually doesn't change. This is another like Muppet vision. Again, as you move from 90 degrees out towards the 26.7, that 5,000 mile is descending at the same time towards the horizon with you. And that's not depicted in this sort of graphic. As you move away, it's coming down. Just like if you move away from a tall building, it shrinks behind you, comes down.
Exactly.
Same with the star. As you move away from it towards the horizon, say, or towards the so-called equator, every step you take, it's coming down, 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 down.
Yep, exactly. And that's the problem that I have with it too. It doesn't show that. Polaris's height stays at 5,000. What you see in your vision is it dropping, just like you said.
I mean, just go pick out a water tower anywhere near where you live. Anybody who's listening who doesn't understand how this works, go pick out a water tower and start directly underneath it, and then drive away from it on a highway or whatever, and just keep driving and watch what happens to it. Does it stay directly above you? No. It goes down and down and down as you get further and further away. That's what happens to it.
Yep, exactly.
The only thing that would be different about the star is that the star happens to be up away from us and in an area that it could theoretically or possibly have an infinite amount of leeway in degrees, basically, in which case their picture doesn't match or count anyway, because we're talking about something that we literally can't experience on Earth with any sort of experiment or similar thing, because it's up in the sky and we aren't.
And besides, as it descends, as you move away from it, the 5,000 kilometer, it's descending. It's moving into more and more visual obstacles, from cloud tops to dust and other atmosphere, which is thicker, more dense, causing it to be less visible.
Yeah. Okay, I see we've got Crow XE who has joined us, and Travis the Plain Truth. What's up, guys?
Yeah, hello.
Hey, Crow, I think
Sorry today. I came late. Sorry.
Oh, no problem. Thanks for coming. I think you're a proponent of this particular flat Earth debunk. Is that right?
I'm not sure exactly what this is, but as far as I think, it's to demonstrate the change of angles according to distance, and I see the change is not relevant to what we see on a globe or in reality.
Yeah. So this is a common debunk for Polaris that Ballers put out. Polaris on a flat Earth. That's what this is showing right here, that the angles don't match reality, correct?
So at 90, I mean, I think the last line is like 10,000 kilometers, I think.
Yeah, each one of these lines is, I don't know what is it, 100 and, I can't remember the exact in kilometers, but it's 690 miles. So this is the equator right here in this diagram.
Yes.
So 1 degree per section.
We see in reality.
Yeah, this is what
the Polaris, and and it would be 45 degrees when you're 5,000 kilometers away. But after that, it will not match.
Okay. Well, and did you hear what we said about perspective? That this doesn't match how we actually see.
According to perspective, yes. If you move away from something, it will drop in angle, and that's what we're looking here. That's what we see here. Ow.
Uh-oh. What was that?
Can you guys not hear me?
Brian?
Oh, we
I can
can.
hear you.
We can. We don't see you in Discord anymore, though.
Yeah, I had to drop and come back because I was trying to talk and it didn't. I guess you guys couldn't hear me, so I had to drop and come back.
No.
Gotcha.
So I said hello when you said. I said hello earlier when you said hello, and then since I've interrupted anyway now, Crow and I have had this discussion before, and so my question is this, right? Basically, you can't measure an angle. I'm in New York right now. I'm outside of New York near Brooklyn, and I can see the skyline, right? So I can choose any of those buildings, any of those skyscrapers I want. And I can measure my angle to it from my distance. And if someone else is another 10 miles away or another 30 miles away or whatever, we should be able to say the same thing, that getting the angle to those skyscrapers is impossible on a flat Earth. Okay, so all that means, though, is that if I measure my angle to it, right? This is the whole thing about a joke that I made up that I would love to have cartooned by somebody. But if I measure my distance or my angle to a skyscraper, and Crow does as well to the same one, but we're let's say at different distances or whatever. Or no, it would have to be the same distance. I'm sorry, I'm making this up off the top of my head. It would have to be the same distance, but we're at different locations, right? He would have a different angle because he would have to impose curvature. But I would get an angle to it on a flat Earth. I would get an angle to it on a flat Earth, just not yours. That's the same thing with this whole Polaris thing. That's what I've said from the beginning. When you guys say, "Oh, that you can't Polaris," I'm like, bro, do the same thing with a skyscraper. You're going to have the same result. The only thing is you have to bring in the curve, which would have to change your degree of angle.
You do the same thing with trees. You have a little device you hold in your hand. You measure a specific distance from the base of a tree, and you measure the angle to the top. You do 3, 4, 5 triangle math, and you can tell, without chopping the tree down and measuring it, how tall it is within an inch or two.
Yeah, but you'd be wrong, Jim, because you didn't incorporate curvature, bro.
I know, all these flat swamps you work in and stuff, and acres and acres of forest you appraise in Georgia and stuff and go through. There's a curve on all of them. The trees, actually, you can see them fraying away from each other. They're like the hair on the crown of your head.
So I mean, this discussion should go no further. Crow, come on, you
Absolutely,
have to.
it's nothing.
Who was it that did this the other day? We brought it. It was Ali B, right? It was Ali B who asked George. He asked him what the equation was. He said, like, what is this equation? Something d squared, blah, blah, blah. And George said, well, that's the equation that surveyors use to get the curvature. After they measure the distance in the elevation, they impose a mathematical equation that curves. That's bullshit, bro.
Yeah, that's my contention too. Now, I do want to ask Crow a question about this. In reality, Crow, at some point, if we moved far enough back, here's the equator. Let's say we went 2 times as far or 3 times as far. We would look 90 degrees and Polaris would be at the horizon, correct? In reality. There would be some point we could revert back up to where we would see Polaris drop all the way down to the horizon and be at 0 degrees.
Hold on. You're breaking up
Oh, you're
to my phone. Yeah.
you're robotic.
Yeah,
Crow.
give me 5 minutes.
Sure. Okay. All right. Well, yeah, that's my point about this is it's just not valid because this line never drops to 0 degrees. And let me move on to this and we'll come back to that question for Crow. This might be a little small. Let me see if I can make it bigger. But I found this in a old book on perspective for artists. And essentially what it shows is the difference between what we're talking about, reality, the geometric reality of things, the physical actual reality of it, and the way we see it. And we all know that our perspective, in perspective, we see parallel lines converge. But if we were to draw these railroad tracks on a piece of paper, geometrically, we would draw two straight lines. When in reality, what we see is this, and that's what we would measure if we're measuring using our sight, is what we see. That's what we're talking about when we're talking about measuring the angle to Polaris. We're measuring what we see. We're not measuring the geometric reality on paper. Crow, you back?
Yeah, I'm back.
Okay, cool. So my question was, in reality, back to this one right here. In reality, if we moved back far enough, okay, in reality, Polaris would go down to the horizon eventually. I don't know if it would take 2 times as far, 3 times as far as shown in this diagram, but at some point we would see Polaris on the horizon and maybe even not distinguishable depending on how far we were. Is that correct?
Yes.
Okay, but if we drew that into this diagram, let's say we went out here and kept drawing, that will never happen on this piece of paper. If we double
you need
this,
a lot of distance.
it would take an infinite distance. We will never measure a 0-degree angle to Polaris on a piece of paper like this.
Yeah.
As long as we have the height at the height of this line. Right?
Yeah.
So in my opinion, that right there falsifies using this kind of diagram to show these relationships between what we see, how we view it, and the angles that we measure those things at in our perspective. Would you agree with that?
Well, I think the diagram explains how things would look like on a flat Earth. And you've just said that in order to see Polaris at 0 degrees elevation angle, you'll have to be like infinity or a few millions kilometers away from the center.
How would that be determined exactly? How it would look on the flat Earth? If we don't live on a flat Earth, how are you determining how something would look if we did live on a flat Earth?
You have 2 ways. You either use geometry concepts or do practical demonstration.
Well, hold on. That's my point, is that doesn't match reality. That diagram does not reflect reality. That's what the point of this was. If I drew this on a piece of paper, I could never draw it long enough where the two would touch. But in reality, we see them touch. We do not see as we draw on a piece of paper in 2 dimensions. Same with this.
Right.
Let's look at the railroad tracks. This is the same situation. The guy's standing above the railroad tracks. 0 degrees is always going to be 6 feet above the railroad tracks. But what he's going to see is the track up here. So that means you can't represent visual reality with this kind of diagram.
If what you draw on paper is automatically something that can be in reality, that picture of the infinite stairs is real. We can make that in 3D. We can do that for real. But we can't do that, can we? Perspective matters. And the medium that we're using to demonstrate matters. You're not using reality when you draw a picture on a piece of paper. You're using a model or an example or a cartoon or whatever. You're using an image. You're not using reality to demonstrate reality. You're using your imagination in an attempt to explain reality.
Now, from the dawn of history, we've been drawing things and we produce it. So this is very, very bad, what you're saying.
What do you mean?
No, it's not very bad.
Hold on.
What I said was 100% accurate.
You never responded to my point, though. You made the point about that is how we represent what we see, but and that is an accurate representation on what it would be on a flat Earth. But even for this railroad track, this guy's standing 6 feet above it. He's never going to measure a 0 degree to the top of these railroad tracks, but that's what he's going to see. He's going to see it touching the horizon.
Yes, because you don't need exactly infinity distance, but you need long distance comparing to the elevation.
I don't think you do.
So, yeah, so how far is that point that he sees on the railroad? 6 kilometers, maybe 5 miles or something like that. That's enough to make the angle close to 0.
All right, let's look at this one. This shows some different buildings. This is a perspective picture. You'll notice a few things about this. They all go down to a vanishing point that's somewhere around here. And the lines are angled according to the height of the object. The higher it goes, the higher the object, the more steep the angle. Until directly in front of you, you got this building that's 90 degrees up and down. Everything vanishes into this vanishing point. Now, this building, long before it goes over a curve, is going to be directly on the horizon in that vanishing point, and you will measure 0 degrees at some point. You do not need to go near infinity or as far as this diagram would have you believe in order to get the object to be at 0 degrees on the horizon. That's just not true.
Yeah, but as you said, it will be very long. Doesn't have to be near infinity, but very long distance.
Look at this.
Like
this is
outside
what,
of the
15
flat Earth.
feet high? Something like that? If you follow this line down, how far until that's at 0 degrees? Look at it right there.
I don't see it in the...
That's only
Okay,
2 or
hold on.
3 blocks. You don't see it in... I'm sharing in the Discord.
Yeah, okay, I see.
Which one are you talking about? The lamppost on the left or what?
I'm talking about this line right here, which follows this kind of. So this is about 15 feet high, something like that. 20 feet, let's call it.
But
Look at how
hold on,
steeply
the
that
horizon...
goes down, Crow.
Yes, okay, so... The horizon line itself doesn't seem to be on the same eye level as the observer.
Yeah, exactly. It looks like it's elevated, right?
Yes, I look at the building and it looks like higher than the eye level. So there's something wrong with laying the whole angles on this image.
No.
Or maybe
no, there's
it's not
not.
clear.
No, dude, I'm following the perspective lines on these buildings and they all point right here. That's how I drew them. I took a line and I followed a straight line off of these buildings because that's what perspective does. It makes everything slant down to a single vanishing point in the distance.
Yeah, I don't have an objection on that. I'm just talking about the first line at 0 degrees, the horizontal line. Is it at the same eye level as the observer?
Yeah, I think so. I mean, even
Because
if it wasn't, let's say even if I moved it down here, what does that do for us?
No, I just see my eyes seen something that I thought it's wrong, so I thought to point it out. It's too high comparing to the cars, and the cars are not that far. But yeah, well, anyway, so the building, how far away that vanishing point would you see it?
Well, it looks like it's about 1, 2, 3, maybe 6 blocks. So you're talking about 0.6 of a mile. Maybe a mile down the road, the vanishing point is there for this height. Let's call it 2 miles. But I want you to notice something. These higher buildings, where's the vanishing point for them?
Okay, if we say the vanishing point is 2 miles and the height of the building, what, 100 feet, something like that?
Okay.
The closer ones. So if those are Polaris, then compare the 5,000 miles or 3,000 miles of Polaris with the 100 feet and the 2 miles, and you would get the distance where you stand outside the flat Earth in order to see Polaris near the horizon.
No, I don't think so. You're still
I might
thinking
just
in
jump
pure
Where
geometry.
do we get the height of Polaris from?
Well, pure geometry
Someone fill me in on that?
describes
Yeah,
reality.
we don't have the height of Polaris. Basically, what we have to do is
Yeah.
suspend disbelief, and
Yeah.
basically, just to have the argument, we have to say, okay, yeah, you measured how far away Polaris is, even though it's literally impossible for them to do that.
So,
And
so I
then we
can
can
get this
have the discussion
equation
that
and
is
put
worthless.
any. Yeah, Bob, we can put any numbers we like into this equation until we get it to balance to what we want it to be.
Yeah,
If someone
it's
can
rough to
show me
start
the height of
with,
Polaris,
assuming, an
then we'll talk
altitude.
about it.
But I think the more important point about that image
Yeah, more
is,
important
let's
than the
say,
reality.
a practical
yeah.
example. If you look at radio tower or something like that, and you move away from it certain amount of steps, you measure the angle. You move the same amount of steps again, and you measure the angle, you'll get a certain shift in degrees. If you continued again the same amount of steps, you should get the same amount of degrees if you are on a curved surface.
Well, let me tell you something. What is it that's a function of? And that's part of what I'm trying to show with this diagram. It's a function of the height of the object that you're talking about.
Yes.
They all go down to the same vanishing point.
Mm-hmm.
So what you're going to see is this building is going to recede in the background, right? And get smaller and smaller and smaller and smaller. But if we were seeing it from the side, it'd still go down to the same vanishing point. You're still going to see that measured along this. Now, I guess the crux of the argument is how far before it goes down to the vanishing point. But can we agree that this diagram is bullshit?
No.
Then we
because
can
of
actually
two
talk
reasons.
about something, reality, not this.
You talk about the image of the buildings.
We'll talk about the image of the buildings and talk about what we see in reality and how we actually see. But this representation of reality, can we agree that this does not take into account how we see visually?
No, the image looks okay. Vanishing points, perspective. I don't see anything wrong with it.
So let's say I took this building and I put it on that piece of paper instead of Polaris. How far would I have to draw that out before I got the 0 degree down at the vanishing point?
Well, let's say 1 degree. It doesn't have to be 0. We'll just make it 1 degree. You can do it by, actually like getting a string and pull it on top of something and go far away and measure the angle. Or you can draw it a side view on a paper. The results will be the same.
But things do go down to a vanishing point. We see them go down to a vanishing point. In this type of model, in this representation, you will never have something at 0 degrees.
Yes, on a flat surface, you'll never have exactly 0 degrees, no matter how far you go away.
Right. So this is not an accurate representation and not an accurate debunk of what we would see in reality on a flat plane, correct?
No, it's not a representation of what we see in reality. It's a debunk of the claim of the flat Earth. I think that's the point of the diagram.
It's a poor
This is what we
debunk.
should see in a flat Earth.
It's not a valid debunk.
You're twisting it, Crow.
Right. Whether we live on a ball or live on a flat plane, we should be able to both agree that no matter what the shape is, if we keep moving away, it should eventually go down to the horizon level either way, no matter what shape it is. That should be happening in reality. So that means this paper cannot represent reality. The diagram can't, because it never gets to that point. So it doesn't
see it to
either
infinity.
reality.
Well, the paper doesn't represent reality. It humors the flat Earth claim. That's what the paper is doing.
It does what? Humor it?
Yeah.
We
The
don't
Earth is
need
flat.
humoring,
Okay, here's
bro.
Polaris.
Thank you,
Now
though.
here's the angle.
That's the problem, is that it does not humor a flat Earth plane. What it does is makes up an entirely separate concept and then calls itself a flat Earth plane and then proceeds to attempt to debunk something that it isn't representing. That's what
It's called a straw man, Crow.
Okay, you get a 5-inch block, put a string on the top of it, and pull it far away until that elevation angle of that string is 1 degree. And tell me how long it's going that to be.
It's got to get to 0 degrees. And 1 degree is going to take a long way. How far do you think it would take 1 degree with this 5,000 kilometers? A ridiculously long way. We don't see like that. Things drop down.
Well, do practical experiment. Do it to prove yourself
Based
that
on
the
your
angles that you
flawed,
can.
your flawed design of how things should operate. It's not based on visual reality. That is not how our vision works. Why would I do that?
Well, this is what I'm telling you. I'm telling you, do practical, like real objects, and measure the elevation angle of these real objects. But before you do that, make the prediction first and see if the prediction is going to match or not.
All right.
Prediction based on the geometry.
All right. Well, I can't get you to
We
say
need a
that it's a lousy
volunteer for that.
debunk, but I thought I'd give it a try. I see that Rakia joined. What's up, Rakia?
Hey, good to see you.
Good to see you. Do you agree with what's on this page, though, Crow?
Hold on. Which page?
Well, if I'm going to draw these railroad tracks and I want to represent reality, I'm going to draw it this way and not this way.
Yeah, yeah. I see the tracks.
Right. So why is this different than Polaris coming down or a skyscraper going down? This goes to a point, it hits 0 degrees. Why is that different?
The difference is those rails few meet each other.
Oh, your mic's a little low again. Yes,
Yeah,
those
he's
will
extremely
these
quiet
will meet,
suddenly.
and this matches reality. In reality, they will meet. Now, if I drew them on paper, like, you know, using this method, I would draw one line here, and I would draw one line here, right? And they would never meet. Never, never. I would end up with something like this. And if I wanted to draw angles to, let's say, from here to here, or here to here, or here to here, those would never match the reality, because in reality, the angles meet. They don't go straight. The parallel lines meet in our vision.
They on the image they appear as if they meet, but if you zoomed in,
That's what we're measuring, though, Crow.
Yeah.
When we measure angles, we are measuring how things appear, not the physical nature of them. This is the physical nature of them. This is what we see, and this is what we measure when we measure the angles to things.
I said when you zoom on the image, you can measure and
Okay.
between.
Maybe this is a better way. Crow, do you see that bottom middle picture that shows, it says, and so the man sees the track this way. Do you see that picture?
He's
I
talking
can't
about
hear
this
him.
one right here. Let's see if I can make it a little bigger.
I can see it.
You see that down there where it says that?
I can see the picture. I can.
Okay, can you measure the angle between those two lines? The ones that go off into the distance. Can you measure what the angle is on those? I can't hear him.
It's a
Tell me
distance,
what he's
not
saying.
an angle.
I can't turn you up anymore, Crow. Maybe you're having a mic
How about
issue.
that?
I'll try turning them up on mine a little bit here. What was that, Crow?
I say that's a distance. You cannot measure an angle on a distance.
Right now
I mean, the
on this piece
distance.
of paper, there's two lines that go off into the distance, right?
Mm-hmm.
Could you figure out what the angle is between those two lines?
0, because they're parallel.
On this piece of paper, you're telling me those lines are parallel.
Oh, okay. I would say maybe 60 degrees.
Okay, all right. So that's not reality, right? Whenever you're looking at train tracks, even though it's going to look exactly like that, and you could eyeball degrees on it, in reality, you could try to. In reality, those lines never actually meet. That's the problem. It isn't properly representing reality, even though it kind of looks like reality might look. And that's the problem with the other diagram, is you can get an idea of what it kind of might look like from that diagram, but it's not properly representing reality. See this picture here that's supposed to be showing me an idea of what reality looks like? I could get an angle off those two lines, because guess what? They do meet on the piece of paper. There is an angle there. But I could not do that in reality, find a real angle, because just like you said, they're parallel in reality.
Yes, and whoever drew this diagram made them actually meet at a single point on the horizon. But
Just
in
like
reality,
they do according to our eyes in reality.
Yes, but what's the measurement of the angle that you can see with your eyes?
Exactly. That's the point. Exactly. So you're there. It's just a matter of whether or not you'll admit that you're there or not.
It's the vanishing point anyway, at the end of the tracks where they meet.
Okay, so how about this? A building one floor in the desert. How far do you have to go away from that building in order to see it squashed to the horizon
Not very far.
due to.
Not very far. It'll meet the
It
horizon
does-
pretty quickly
It
here.
doesn't matter how far. Do you agree that eventually it will squash into the horizon, Crow? Do you agree with that? Okay,
Yes, I do.
So that means that the picture that was shown before, the diagram that was shown before, absolutely cannot represent reality because it never squishes into the horizon. It won't ever.
The diagram, it was not perspective. It was a side view showing the triangle
It was
of
not
our
showing
view.
reality, and therefore it can't debunk reality because it wasn't showing reality.
We measure in
perspective is
perspective. When
only
you are
reality.
measuring the angles to Polaris,
could-
you are measuring perspective. You're measuring how we see, Crow.
I could draw an infinite number of pictures that don't show reality, and not one of them would debunk reality. Not a single one.
I don't know how to convey this except for do a practical example with certain objects and you will see what.
These are practical examples, graphically illustrated, very clear and concise.
No, they're just images.
All right.
There's no data on it.
Oh, come on now,
Our
dude.
view of things converging towards the distance,
Well,
like
listen, if you
railroad
accept,
tracks, is our
if you
vision.
accept the argument of just
parallel
images,
reality.
we're done here.
It's different.
Look at this. These aren't don't go very far before they go to 0 degrees, do they?
0 degrees would be a separation between, yeah, I mean, 0 degree on an image means the separation is 0 in distance, in pixel.
If I were to take
Correct.
my what's it called? Not a theodolite, the thing that you measure angles with. I've got one right here, sextant. I was looking on the box for the damn name. Sextant, and I measure the angles of each of these. I'm going to get down to 0 degrees pretty quickly. If I draw that on paper, I'll never get to 0 degrees. Because this is what I am measuring the angles off of. What I see. This is a picture, yes. But in reality, when you're using a sextant, it's based on what you see and how you see it, not the physical geometry of the objects. You can't draw that on paper, the physical geometry, and compare the two.
It's important too that you only take readings on a sextant over the horizon 15 degrees at least. Nothing below 15, it's too compressed.
Yeah.
Well, if you're looking at objects on near around you, away from refraction.
Well, forget lower than 15 degrees. There could be multiple reasons for that. One could be that objects don't go all the way, down like Polaris. It doesn't actually touch the Earth at any point. It's probably the atmosphere and refraction and whatnot. But the bottom line on that is below 15 degrees, we can't trust the measurements anyway. So all we have to do is be able to measure from 15 to, say, as far as I'm concerned, 75, 80. Right? That's all you guys can do. That's all you can show us.
Right, for navigation and the use of a sextant on, I guess it's a 600 square mile plot of ocean that you use it with. Flat ocean too.
Right. Okay.
Okay, so last question. Again, with the building 10 feet high, how many feet would you be away from it in order to see it to disappear?
Maybe 1,000 yards. It depends on the day, how much like dust and those waves and other stuff are in the air. There's so many variables. You can't say every day at 1,000 feet the house disappears.
In average.
It's a possibility.
So in average, 1,000 yards.
Oh no, I gave you an example. Don't hold me to
500?
it. You want to see a bungalow disappear, find a bungalow in the middle of the desert and walk away from it. Or be more practical, find one that you can see for a long distance with no obstacles and walk away from it. And tell me how far you are when it disappears. It will disappear and shrink. The farther you go, the more it'll shrink and disappear. Brain dead.
From my recent, okay, if you don't have an answer, I have an answer, maybe if you like it. From my very recent experience, I was on a highway, straight, a bus away from me that was around 1 kilometer. See the bus clearly. The bus is 4 meters. So 4 meters, I can see still 4 meters. This angular size for this 4 meters within 1,000. So that would be the ratio that you have to walk past outside flat Earth in order to see Polaris.
I wish I knew what the hell you were talking about.
Okay, so I've got a triangle calculator up. So your question was, how far away would we have to be to get to 0? I put in 0.5, half a degree. So this is a 10-foot high, right? So B would need to be 1,145 feet, supposedly. So what does that tell us, Crow?
Well, that tells us the ratio between the distance from equator to North Pole in relation to the height of Polaris.
On a flat.
That big number that you came up with on a flat surface. This is supposed to be the distance from the equator to.
Right. This is using your basic geometry that you guys always use. So let's see what 5,000 would be. 573,000 kilometers if Polaris was 5,000 kilometers high to get to 0.5 degrees. Does that seem right?
No.
No.
Why did you put a relevant number? The distance from the North Pole to the equator, but use the reverse stand in order to get the altitude.
Isn't that assuming your values to begin with?
Yeah. Well, let's just look at this.
Yeah, Brandon, what if Polaris was 2 miles across and 100 miles in the air? I mean, you can just punch any numbers you like into this equation until you get the answer you want to give you the narrative that you want to punt.
Right.
These guys reverse engineer their mathematics from the answer backwards. Sorry if I got background noise.
Yeah, I mean, this is, again, to bring up a previous conversation that I've had on this show with Crow at least 2 or 3 times. And to my knowledge, Crow, you haven't stepped up to the plate, okay? Where do you get your value for the radius or the circumference, okay? The only way that you're going to get 69 miles per degree is to have a value to divide 360 ways. Where did you get that value?
Well, that would require you to agree that the Earth is a sphere in order to.
No. Hold on. I'm sorry. No, I've done this with you 3 times, and again, Crow, you haven't done anything with it. Why not? I've asked you now 4 times. Here it is, the 4th time. Where do you get your value?
Value of what?
Either the circumference or the radius. You pick.
Circumference of the Earth? The spherical Earth?
The one that you claim you live on. It's your claim. Do you believe you live on a ball?
Yes.
Okay. How big is it?
6,371 kilometers.
Great. Who measured that? This conversation should go no farther, ever. Who measured that? Did Eratosthenes, did he measure that? Because he got pretty damn close, right?
He did with some
No,
clothes.
he did not measure. No, he did not measure the circumference. No, he did not.
So what did he measure?
You tell me.
It's your story, Crow.
He stuck a stick into the ground. He looked down a well. He measured an angle. That's all it's going to give you. This is what we're telling you. When you are doing surveying, you're only going to measure distance and elevation. That's it. You're never going to get curvature. You can make the curvature like Effie Evangelist just said. You can give it any value. You could have made the Earth 10 million kilometers, and you're still going to get the same degree. You just have to move your shit around, bro. This is all prefabricated bullshit. You don't.
It's a shell game. It's just a shell game, Travis. They just keep moving the shells around, keep the P out of control.
I know.
Nobody
I know,
knows where it is.
Yeah,
switch it up. Yeah.
but again, we don't have to take this any farther. You guys don't have physical measurement. You have a concept, you gave it a value, and then you divided it by 360. That's it.
You can't either get physical measurement for flat Earth.
Excuse me?
Cannot get flat Earth.
Yeah, we can. Yeah, we can.
Yeah, well, show me it.
Okay, look. What's the? You want to go by kilometers or miles? Right. So we have a preset value, either in kilometers or miles. I'm going to start at the edge of the Atlantic. I'm going to drive to the Pacific. I can measure that. You know what I'm going to get? Distance. That's it.
But this wasn't yet
This wasn't yet what?
done.
I believe that there's relative accuracy as to how far it is from Atlantic City, New Jersey to LA. Pretty sure.
Well, okay, if it was done straight road, that would a flat Earth.
Wait, straight roads? Why? Why can't you just take the mountains? You got to go over a mountain. You're not gonna take away the distance that you're. If the distance from one side of the mountain to the other is 10 miles, but your elevation is 11,000 feet, you're gonna have longer than 10 miles distance. Okay. All right. So don't reverse the burden back on us. Don't say, well, you haven't measured a flat Earth. Bullshit.
Well, no one did. If you have to measure it, you have to use better way, more accurate triangulation.
Why?
Because it's possible.
Because what?
It's impossible. No one ever done it. No one will ever do it.
Okay, so Crow, if you went to Google Earth, or even if you went to an atlas, right? Okay, you're back in the 50s. You're gonna climb into the station wagon with your family and your dog, and you're gonna trek across the United States. You don't think you can use the legend at the bottom of your atlas for each state and calculate how far you're going to travel? You know how they were able to do that? Because someone drove.
Country.
Excuse me?
It's only within one country. To go to the other continents and oceans. How are you going to?
We're not measuring anything but the land itself. So I don't know what your problem is. Okay, again, listen to what I'm saying. If we're in the United States, or if you want to put us anywhere else on a continent, if we're in the United States and we jump in on the East Coast and we drive across to the West Coast and we use the legend, we can see how far we're supposed to drive. And then we're going to drive that far.
Yes, okay. No problem for one
it.
country. But
that's
you cannot measure like from Seattle.
Okay, look,
Morocco.
Crow.
Let me interrupt for just a second. I apologize.
Yeah, go ahead.
Esteban Ibaka, 2,500 CLP super chat. Thanks, Esteban. Question: why does all measurements and calculations provide the same value with a margin inferior, margin of error? Different instruments and methods all agree. Why? Go ahead, continue. And Gadget Inspector came in with a $5 or a £5 super chat, or €5, excuse me. Thanks, Gadget Inspector. Go ahead.
Okay, again, Crow. Do you at least imagine again if you are on the United States, if you're on the East Coast and you've got an old school atlas, or an old school atlas, and you're not going to use GPS, you're going to go, I'm going to go old school. We're not even going to take our cell phones. We're just going to drive. We're going to use the odometer, and do you feel like it would be within a margin of error that you're going to be able to calculate how far it is from the East Coast to the West Coast and then drive relatively that distance? Just in answer that question. Do you feel like within a margin of error, you're going to get close to what the Atlas says you should?
Yeah.
Okay, great. That's it. Why do you bring up other continents? That's got nothing to do with it. If you want to measure those other continents, it's the same principle. Okay?
Because
But now, but
you
again, hold on again. You're reversing the burden. Okay? You're taking away from the fact that you cannot
I'm not
validate.
reversing the burden.
Yeah, you are, because you said you can't measure the land masses on a flat Earth either. So that is reversing the burden.
No, I was just pointing. You don't have to measure everything physically to get.
If
you want to say the other thing is absolutely not true.
That's right.
If you're making the argument that you're making, you do need to show it. That's what proving it is, dude.
Okay,
Right.
how about measuring the
How
distance?
can you
any
even hold that
target
position,
using
Crow?
a compass?
It's so dishonest.
No, you can't ask us any questions, Crow. You have made a claim that you believe. You were just going to ask us a question.
No, that's not a question. I'm just telling you about one of the ways used in the army to measure distances, which is the compass.
Yeah.
So you measure the azimuth of a target, you move few feet or few yards or whatever, you measure the angle again, you get difference in the readings, you do some triangulation, which you say it's my math or globe math, you get a distance, you fire, you hit the target.
You're not going to get a globe out of triangulation on a flat Earth.
No, I absolutely did.
How did you? Okay, great. That's what I asked you. I asked you where you get your. So tell us, where'd you get your value?
The first value is I need a distance first.
A distance of what?
An arc on that globe.
An arc? What the fuck do you need an arc for?
Because any line on the globe is an arc.
We're on a fucking globe already. How did we get on a globe, Crow?
You didn't hear me.
Yeah, I did.
Okay, so I need a distance. The first thing I start with is a distance, like Eratosthenes. He also needed a distance.
He didn't.
But okay, I used okay, let me explain my way and then object at the end. So I look at the flight route from Qatar Doha to Auckland, New Zealand. I can't remember, 13,000 kilometers, something like that.
Okay, you got 13,000 kilometers. Great. Just do that. 13,000 kilometers.
Yeah.
That's a straight line.
Yeah, you can. Yeah, just, great circle, not straight line.
I'm sorry? A what?
Great circle.
Where did you fucking get a circle, Crow?
You said we're on a globe. Give me its radius.
No, I didn't. No. I didn't say we're on a globe, okay? You are measuring distance. You've got 13,000 kilometers. That's a straight line.
Oh, that's
how do you know it's curving? How do you know it's curving?
Well, now we're not talking about how did they measure the radius of the Earth. We're back to proving that the Earth is a ball. That we're back to square zero, like the same 4 questions you asked before.
Crow, if you have 13,000 kilometers, which is a straight line, how do you get it to arc?
Because the Earth is...
Crow, you are assuming your conclusion. You haven't proven anything. You're just simply saying because the Earth's a ball. How do you know?
So let's drop talking about the radius and we talk about proving that the Earth is a globe first before you ask me about how did I get the radius.
Look, I gave you 2 choices, a radius or a circumference. You said 13,000 kilometers. I said, great, that's a straight line. You then said radius. So you're the one bringing that shit in, not me.
How do the circumference of a circle or a ball is measured? It's distance.
You have to have a circle already. You have to already know that it's a circle or a sphere. You create it, okay? Listen to me. If B-Ball for Life is in the chat right now, and he's got a basketball, he can math the circumference and the radius because he has a physical object to measure. When you're on the Earth, you can.
And therefore not to be taken as reality.
Hold on.
No,
hold
it's
on.
proven. You just don't know of it.
Hold on. You just made a claim about a fallacious comment. Can you please restate that? What you said was fallacious?
If you say that any measurement that are not based on physical measurement.
I hate to interrupt you guys, but I got to catch up a little bit here. Sorry about that. I did miss a super chat from Esteban El Baca. He says, radius, arc measurements done by surveyors that agree with ancient methods. Same value has been measured and calculated and compared. All match. 2500 CLP. Thanks, Esteban. Appreciate it. If anybody wants to respond, they can in a minute. Gadget Inspector says, Brandon, you're doing a great job. Bravo. Thank you very much, sir. I think A-T-O-I... Atois? French. Must be some French stuff. I am completely illiterate when it comes to any other languages. Thanks, Gadget Inspector. And he sent one more. 20 euro super chat. Thank you. Towards your new camera, Ranty, show us the truth. Much appreciate the support, guys. Go ahead, continue. Apologies for the interruption.
All right, just to go back to your claim about making a fallacious statement, okay? This goes back to our talking cross purposes, right? We're going to have a failure to communicate unless we have an agreement on our terms, okay? I would speak for the panel, I suppose. Anybody can correct me. We would say that we must be able to measure something physically in order to accurately determine its distance or elevation.
Tangibility, absolutely.
If it's not physical, it's not a measurement. I mean, that's just you're
Okay.
describing a different thing entirely.
Right. So again, that's what I'm trying to bring Crow back to. You're going to challenge us on that, Crow, because in your world, you have to deconstruct physics and create metaphysics, create ideas that don't need physical measurement. Now, you can operate in that world, but we're not going to step into your world. We're not going to let you do that, because in order for you to tell me that you're 5'7", I've got to physically measure you to verify it.
Yes, I'm in
You
front
can't
of
do it
you.
just-
You can do it. There's no need to do any funky methods in order to measure my height. But in some other cases, like in rudder, moving plane,
You
how would
can
measure the
port
distance to a
measurement
plane
with
that's coming towards you?
calculation, Crow. Just because you calculate something, that is not the same as measuring it.
Also, I gave an example. Just
Tell
look
me
it up
we-
in Google. Measuring distance using a compass. Measuring distance. Just look it up in Google.
Why can't we take your height using like 2 sticks or 2 L's and we'll get shadows off it somehow? Like, can we get your height using a shadow?
Yeah, that's kind of what I said. I said because I'm physically in front of you, it's easier to measure with a measuring tape rather than doing some
The
funky
difficulty
ways.
of your proof is not our problem. That's your problem. If you want to make a claim about the size of the Earth, the whole Earth, and you make the argument that it's too difficult to measure the whole Earth, so we got to come up with pretend stuff, that's your problem, not our problem. Don't make the claim if you can't prove it with actual measurements. That's the solution to that problem.
Because you want to obfuscate the whole thing by denying this method of measuring.
No, I'm not going to let you say that. We're not the one obfuscating. We're the one.
Hello?
Wow.
Oh,
Wow,
hey,
was that
Silent Zero.
God?
Got a little bit of background noise from you, but
We're not denying
there we go.
your method of measurement because it's not a method of measurement. It's a calculation. That's what we're saying. We're denying that it's a measurement at all.
We're bringing it down to the simplicity of physics, okay? If you want to measure your shadow and say that your shadow equals your physical height, but your shadow is twice the length of your physical height, it's not going to match. The only way to verify that is to physically measure your body. And then when your shadow equals that distance from your feet, then you've got a right triangle with the hypotenuse a squared b squared c squared, right? Okay, that's the only way you can verify shit.
Well, so you're saying that I have to walk physically to the enemy to measure the distance and say, hello, enemy, sorry to bother you. You get the distance and then you get back and shoot. While
No,
you can do
no, okay, no. Listen, if you're gonna make something up off the top of your head, you've got to be more specific. Don't just make some shit up, okay?
I said look it up right now. Measuring distance using a compass. You will find it.
Can you guys hear me?
Yeah.
Yes.
Can I give an example of something good? Let's say, Crow, that I'm gonna sell you a piece of land, right? And I say, well, I calculated that that piece of land is 1 mile per 1 mile, and you're gonna pay me this much, right? Will you pay me for that piece of land without corroborating the distance that I calculated?
The Earth is not 1 mile by 1 mile, and the enemy is more further than 1 mile.
He missed the example. I don't know if somebody else.
No, I don't think he missed it. I
it.
think he's purposely not answering you because he probably understands
Yeah,
what the
that was
conclusion is and doesn't want to admit it.
That was absolutely
because I
obfuscation
made
right
my
there.
point and all of you are jumping away from it.
No, you did not make your point.
No,
Measuring
we're saying your point is
distance with a
stupid.
compass.
Okay, here's the
Measuring
point.
distance with
I
a
got
compass.
it. I
Look
got
it
it.
up.
I got it. I got it. Crow, how do you check to make sure your calculations are correct?
What do you mean?
Okay, so let's say you calculated what something can hold, the amount of weight something can hold. How would you know if that calculation was correct and that that thing could actually hold that amount of weight? What would you do? Another calculation? Or let's see, maybe you would have to do the actual measurement. Dun da da da. So this is what you're doing, Crow. You're
Well, if you
you're
cannot
calculating.
if you cannot
coming
weigh
up
a
with
mountain, what do
something-
you do? If you cannot
Yeah,
weigh
you're
a
coming
mountain,
up
what
with
are you
something
going
in
to
your
do?
You
head.
don't make a claim about its weight, Dorcas. That's what you do. You just don't make a claim about how much it weighs as an absolute. You say it could weigh
Okay,
this
now-
much, or it might weigh this much, or we calculated it weighs this much, and then you don't tell anybody else they're absolutely wrong simply because they disagree with your calculation. That's what you do.
Well, in avoiding my point, you are jumping from fallacy to fallacy. Measuring distance with a compass. Look it up and tell me what
You
it says.
can't measure distance with a compass because a measurement requires a standardized unit. Do you
Look
understand
it
that,
up.
Crow?
Look it up.
Crow.
Look it up.
Crow.
Read
Crow.
and tell me I'm
Can
wrong.
you make a hang on, Crow? Listen to me. Can you make a measurement without a standardized unit?
I'm done. Look it up. Read the citation.
No, you're an
and tell me
idiot.
I'm wrong.
You're
He's
pointing.
done because he can't actually
because
get
you're
anything
stupid,
across.
bro. Come on,
He
just
won't make
admit
a
it.
good point.
Come on,
No,
bro.
that's
measure.
not
You are
valid.
done,
You are
bro.
just avoiding to look for it
Come on,
because
man.
it debunks you.
You're one of the
Right.
honest ones.
Is he
I'm-
talking about
I'm
making a
honest.
measurement with
I've looked
a
it up.
north?
That's not a
No.
measurement. That's looking in a direction. That's an observation. Measurements need standardized units. That is the
I don't-
entire thing that makes a measurement empirical, is because we have standardized the units. An inch
That's
is
your
an inch, no
opinion.
matter where you
That's
go,
an
because
opinion.
it's standardized.
This is an opinion. I'm telling you about a
That's
valid
not an
method
opinion,
used in
it's
the
a
military.
fact. You cannot, if you don't have a standardized unit, fucking keep this. And if you don't have a
Disconnect.
standardized unit and you try and take a measurement, what if it's 5 or is it 6 or is it 5.5? How would you know? You couldn't, because without the standardized unit, your measurement could be anything. That's why they make the standardized units.
That sounds
Come on, bro.
irrelevant to what I'm saying. Look it up. Prove me wrong. Tell me there's nothing that's such.
He
called,
asked you a
measuring
question.
distance.
Okay, listen. He asked you a question to challenge your claim. You made a claim about the compass and measuring angle, and then he asked you a question as to whether or not you can
Just
derive an
evading
answer.
question. Just evading
Hold on,
my point.
Hold on. No. When he asks you a question, he is challenging your claim. Okay, so you made a claim, and he said, "How would you be able to substantiate that claim without a standardized measurement?"
That's
It's just
irrelevant maze. But because
How
we
do you
have to
tell
have
70
meters,
degrees
we
from
have to have meters,
75?
inches,
If you don't
miles,
have a
and things.
protractor that has
So,
a
yeah, we
standardized
all
unit
agree.
of angles, how do you tell 70 degrees from 75? Eyeball it, Crow?
No, we have a measuring device to measure the angle.
Ah, exactly! Exactly! And that measuring device has a standardized fucking unit printed right on the face of it. You're an idiot, Crow.
Exactly.
Yeah,
Exactly.
so you don't make calculations. You use a standardized measuring device. And if you want
Yes.
you do it, hold on. And if you want to do a calculation, you can. But the only way to find out if it's right is you go back to the standardized measurement device.
Which is a compass. Not a
No,
measuring
a compass. What standardized unit of measure is on a compass?
degrees.
No degree. Show me. There's no degrees in a compass. That's a protractor. Come on, Crow. A compass
What?
doesn't tell you angles. A protractor does. You're retarded. You're fucking
Have you lost
stupid,
your
Crow.
mind?
You're
A compass
talking
doesn't have
bullshit.
degrees. I
A
should
compass
record
doesn't
that.
tell you fucking angles. It points at a direction. You're an idiot. So, kick this fucking moron off. He's stupid. He's blogging down the show. He
Well,
says a compass
no,
is a
no,
protractor.
no. He's fine.
I'm just
Crow's
joking.
fine.
I'm kidding now.
But
I'm just-
what do you mean, right the hand, when you say that you can't measure angles with a compass? If you can measure an angle in one direction with the compass needle, why can't you measure that against some standard direction and come up with an angle? Or
The
with a
compass
sextant,
doesn't measure anything.
Compass
I don't know
doesn't
if this
give you
is
an
the
angle.
point.
It gives you a line.
it gives
Right,
you a line,
Okay,
it
right?
tells you
that
direction.
line yeah, and that line is imaginary. Okay, so you can't make an angle with an imaginary line.
Okay, I'm not sure I understand.
get your
I'm not sure I understand
get
your
your-
point, but
Okay, so you have the compass. Okay, if I point my finger straight, am I measuring anything?
no, you're just pointing in
No.
a certain direction.
Exactly, and that's exactly what the compass does. It just points in a direction. It doesn't give you a measurement.
That's all
it's
it
just
does.
a
Yeah.
finger going.
You get your azimuth from a compass. I don't want to take this guy's side or anything, but
No, I'll agree that it gives you a direction, and you could derive angles from it if you set some kind of standard like a sextant has. The horizon is the standard, and that the angle is measured above the horizon.
Well, then you would have to
Like,
say
you
that
could-
your line of sight is a direct, straight, undeviating line.
Right.
Because you can't get an angle with a curved line. But the ballers, they see in the curved path of light. So how do you get an angle visually with a curved vision?
Yeah, and before you joined, we were talking about that those measurements aren't really legitimate because you're measuring what you're seeing and then translating it onto paper. That's what this is all about. Obviously, we see
it's a
something
visual.
like this in reality. It's visual, and when you use a sextant, you're measuring what you see visually. It's not translatable to a piece of paper. At
So
least
the
not in the
question
way
would
they
be-
do it.
Right. So like the question would be, let's take the third tree from the left, right? Counting away from you, 1, 2, 3. Can you calculate the height of that tree from this image?
Yeah, with some assistance, it's possible.
What kind
Okay,
of
great.
assistance?
Why don't you elaborate on that? How much assistance would you need, Crow?
Okay, if I know the height of, let's say, the light pole on the right, and I know the vertical field of view degrees, the height of.
Okay, well, right now the height of the light pole on the right isn't at the same angle as the tree, so they're not going to match.
Oh. I would need something with the known dimensions at the same distance.
Huh.
Huh.
Something that's
Okay, in
already
light
been
of this,
measured,
in
you
light
mean?
of this, hang on. In light of
For
this,
this
can I just
picture,
bring us back to the fact this all started with Polaris. So Crow's now saying that he needs to know something about heights and distances because we had that ludicrous two-dimensional picture that was put up as a debunk against Polaris. So Crow, just remember you need to know some things.
Right.
Yeah, I think
right.
that's an
And
excellent point. Let me
Yeah.
read these couple of super chats from Gadget Inspector. Brandon, never let go. Thanks, Gadget. I won't. And for Norway Ranty, you show us 10 pounds or 10 euros each. Thanks, Gadget Inspector. Yeah, I think that kind of hit the nail on the head. You need to know, what do you need to know? Either the distance or the height. And if you knew the distance or the height, I'm not sure why you'd be measuring the angle to something to try to figure out where it was. But
Right. You already have right. Exactly, man. Exactly.
There it is.
Exactly.
But this has nothing to do with talking about.
Yes, it
Yeah,
does, Crow. Yes, it does.
Well, we don't look in perspective and say, here's the radius of the Earth by looking at the horizon.
Say that again.
I say I don't look at the horizon or to a distant object and say, okay, here's the radius. That's maybe one
Well,
person.
okay. Who said who? Wait, hold on. Who said you do that?
Because that would perspective distance.
I don't know. He's breaking up for me. I didn't hear any of that.
yeah, you're roboting a little bit, Crow.
Yeah, it's a perspective image. You cannot get much from perspective image.
Well, isn't that
And-
what we measure
but
these?
isn't reality a perspective reality?
Yeah, that's what we're measuring when we
Wouldn't
go
the
out with a
conclusion be you
sextant,
can't
right?
get much from a perspective reality?
And you said
No,
you could
we
tell us the
diagram,
height of
look
the
at
tree
things
with a
side
bit
view,
of help.
And then we get the
Say that again, F. Evangelist. I think that's worth going back to.
Crow, you said, we asked you 3 minutes ago, can you tell us the height of the third tree? And your comment was, well, yes, I could with a bit of help. So now you're saying there's something wrong because it's a perspective picture? Man, you just talk yourself inside out as we go along. You probably should have gone fishing today.
All right, we've got a super chat from Anthony Sacante. He says, this is brilliant listening. Be kind to Crow, guys. He is technically helping.
Yeah, sorta, I guess.
Fair comment. Yeah.
Yeah. No, Crow's a good guy. I appreciate you coming in tonight, Crow. I hope you don't feel like we're beating you up. But I think it's frustrating on both sides when we're looking at the same thing and we just can't get each other to accept what we believe is true. There's no way with any of these arguments you're making, Crow, just to be honest, that it could overcome everything that I've looked into regarding how we measure things visually and how the angles work to things. I mean, do you have any evidence, anything we can touch or feel that shows that, you know, vision, measuring angles in your vision equals, you know, how you would write it down on a 2D piece of paper or reality?
Okay, yes. I have one that we can do right now, but of course with paper in. So you draw a line, straight line, say 10 inches, and you put a vertical line to it, 1 inch, and you calculate what the angle is going to be. Then you draw a line, you complete the triangle, and you measure the angle. It's going to match what you calculated. Now cut out that triangle and set it up in reality as a physical thing. It's still the same angle. It didn't change. If you cut out the angle, so you can calculate it, you can draw it, it's reality.
What were
Yeah,
the,
but
what were
you
the
have
inches you said? What were the inches at the beginning that you said? 8 inches and 1 inch?
No,
10
10
inch and 1 inch.
Okay, all right. And how'd you get those inches?
Measure it.
Ah, there it is.
Right.
Thank
Okay,
you.
right now. Right, yeah.
We're not talking about now. We're not talking about measurements. We are talking about something related to the first thing. That's polarity.
No,
perspective, and
Crow.
angle.
No, Crow. Listen. You have a value to start with, and that is 10 inches and 1 inch, okay? Now, okay, how about this? You have a piece of paper. There's nothing drawn on the piece of paper. What are the inside angles of values of that triangle?
I have no 2 lines.
That's correct. So when you put in 10 inches and 1 inch, you are now giving a value of physical measurement whereby you can calculate angles. That's reality. Okay?
Because I said there's something we can do right now. What I can go outside in a specific day and have no clue what's the distance using a compass, and we'll get distances and elevations, angles, measure it after that. And
Okay, Crow. What you're doing right now is giving us a hypothetical that you haven't done. Okay?
I have done.
So,
I've been in the army for 20 years.
okay, Crow. If you're going to take a compass and do what you just suggested, what is the only way to verify your
Sometimes
calculation?
no other way to fight. Sometimes if I'm doing it within my home, I can verify it with
You're
measuring.
changing. Stop changing the shit around, man. Are you out on the field in combat or are you in your house?
Out on the field, there's no way to confirm what I'm doing, except when the shot comes very far away from the target, then there's something wrong.
Okay. Let me
Redo
ask
the
you this. Okay. Let me ask you this question, Crow. Let's say you're out on the field in combat, and you've got a mortar, and you do your calculations, and you go, okay, X, Y, Z, and boom, and you miss your target. Were your calculations correct?
Of course, there's a margin of it cannot be very.
Okay, so again, my question remains: how will you verify your calculation? Okay, the only way is to physically measure or adjust your mortar by degrees until you finally hit your fucking target. But even then, you don't know that you actually measured and calculated correctly. You just happened to hit your target in the right general area. You could have been 10 feet off and still hit your target because of the explosion. You still could have taken out your target. Okay? Listen to us, Crow. We're not talking about making measurements in battle on the field. Okay? That's not what we're talking about. It's very simple. We're talking about geometry, measuring the earth. And the only thing that you can do is measure distance and elevation. There is no curvature.
Well, there's.
Is anyone there?
Yep, I think Brandon.
I was
Yeah,
off
we
mute,
know he's got
and
no
then I
curve.
muted myself.
Oh, okay.
I apologize for that. But let me.
We missed something.
Yeah, I was talking that whole time. So another rookie mistake.
I hate that.
Yeah, it
I hate
sucks.
that.
So let's say we want to measure the end of this road that we see on the horizon with our sextant. And I know it's the bottom, but if there was something on the top that worked the same way, we could use that. But let's just say we want to measure the end of this road. What value are we going to get on our sextant for this spot on the road right here? Anybody?
For elevation
I
angle?
can't.
Yeah,
Zero.
that's how we measure the elevation of Polaris, right? So let's just kind of stay on that. Let's say we're measuring this road instead. What would be the value that we'd get from our sextant for this spot on the road right here?
But exactly where you're.
Oh, the cursor is at the vanishing point.
Oh, it's 0.
Yeah, 0. So how would we
Got it.
represent that on paper as an angle?
From your location, intersect. Oh, parallel to the horizontal.
It would be a horizontal line.
Yeah.
Okay. So there's no angle to that. So that would be completely useless, right? Well, when something is above us and goes down to a vanishing point, and we measure the end of it that's at the point, that doesn't mean it's actually at zero elevation sitting on the ground, right?
Yeah, it could be like this tall building, but at infinity, it's the horizon, virtually at your eye level.
Right. Okay, well, I think we beat this dead horse a little bit, but I see that we got Gleam showed up. Hey, what's up, Gleam? Thanks for joining. And we've got Chad, who popped in. Chad, how's it going? And then I know Silent... Hey, Chad. And then we got Silent Zero, who came in and did say a couple things. What's going on, Silent Zero? All right. Anybody have anything else on this whole perspective thing, or anything they wanted to talk about?
I still am going to hang my hat on the fact that Crow has not established how he derives a value of the circumference. You haven't done it.
I've done it, and I tried to say it like 5 times to you right now, and you always interrupt me.
That's because you are declaring that you have curvature without demonstrating how you determined you had curvature.
Well, that's why I said we have to prove that before I go in. But here's the funny thing. I used the most funky way to measure the Earth radius. No one ever done it. And I came 1%. How?
You came what?
With the most funky way to measure the Earth radius. No one ever done it before. And I came accurate within 1% with the...
Great. What are your values?
Something.
Excuse me?
He said something.
Okay,
6.
Crow.
Not exactly the same, like 1% off.
1% of what?
No, yeah, you're right. Crow.
Of the mainstream radius.
Okay, Crow, don't tell us how far off you were. What were the values that you had to get you your final value within 1%?
Okay. Azimuth and elevation angle from
Those
cutoff
are not
and from
values. Those are not values, Crow.
and 13,000 kilometers. So I used 5 numbers.
I can't hear him. He's breaking up for me.
Oh,
all right.
So yeah.
Well, that's okay. Let me catch up on super chats. Then you can tell us more about that. Anthony Sacante says, "This is brilliant listening. Be kind to Crow." Oh, I already read that one. You got two reads out of that one. Gadget Inspector with €5. Thanks, Gadget Inspector. €5 again from Gadget Inspector. Wake up, please, people. Yeah, I like that message. Rakila Life, $14.99 US. Thanks, man. Shout out to all the ballers who are admitting atmospheric conditions can obstruct objects in the distance bottom up. Only took years to admit. Bye-bye ball. Yeah, that's an interesting admission. We should ask Crow about that one. Esteban Ilabaca. Since when are indirect measurements invalid or less accurate? You can measure length with a laser to a better degree of accuracy than with a ruler. Anybody care to respond to Esteban or anything else there, or?
Yeah, I mean, you might be able to measure the distance with a laser if you accept that laser as the standard, but you have no way to actually prove to anybody that laser actually measured that distance. They would have to just trust your tool. That's not the same as verifying it yourself. You can choose to agree with the tool if you want, and I don't think anyone was arguing that you're not allowed to do that. But when you want to prove it to somebody else, you don't get to just point your laser at something and say, see, my machine says it's that far, unless they agree to that.
Yeah, I would say doing it with a laser, I mean, we're used to inches and feet and kilometers and stuff. So if you do it with a laser, you don't even know with that over a long distance if you're coming up with anything accurate. If it's bending or whatever, a tape measure, I think a tape measure over long distances would probably be a better way.
I was going to say exactly the same thing, if you can hear me.
Yeah,
we can hear
exactly that.
Hello, Glenn.
Yeah, lasers at that distance to the horizon is crazy talk. That isn't
Yeah.
accurate.
Like I said, yeah, if you got any kind of refraction or that's all.
So if you're building a bridge over 3 kilometers water between the two shores, how do you measure the distance?
With a
I don't know,
theodolite,
tell
step
us.
by step, right?
Done
What do you
in
mean by
sections. But they'd run a
Sections?
barge out there, wouldn't they?
Sections on the water with a measuring tape on the water? I don't think so.
Well,
That's what surveyors come in and they use the laser, the EDM.
Well, let me say
Wait,
something
did you just
about
say
the
measure
laser.
the water?
There was a comment made that you would use a laser because it's more accurate, but those distances have been validated. So that laser was, built, and when they were measuring distance, they validated those distances. So when it says 100 meters, they shot at something they knew was 100 meters away, and whatever the return was, that's what they set the reading to tell you that it's 100 meters, right? They were calibrated.
Well, if Raki is here, maybe he can talk about more. Does he have to measure with a tape every time he do a laser?
Are you trying to measure drop or just the distance from one location to another on Earth? What are we really talking about here?
We were talking about the validity of using equipment that doesn't measure.
You're choppy.
I don't
What'd you
know
say?
why on earth he is so quiet. He was fine
Yeah,
when he
you're-
first came in, and now it's like super low.
Yeah, I
You're
have
low
to
and you're
hold
choppy.
this. I was saying we were discussing the validity of laser laser ranger.
I mean, if you just chuck something in Google, because I'm not a professional, I don't know, but straight away it says laser distance measurer, how far is the maximum distance? And it says one of their devices reaches 80 meters, 120 meters. Maximum distance can't be achieved in many situations, therefore you need optimal conditions.
Yeah, it's not very far. You're not measuring tens of miles with a laser.
Yeah, that's it, exactly.
So
That. So
if
3.5
you mean
kilometers.
only 20 meters or 20 kilometers?
I don't think they'd put any sort of like leveling thing on a bridge anyway. I'm sure nowadays they do it with these big massive barges, don't they, where they feed out like a train track or something like that, and then the whole thing builds itself. But I think laser on, because you'd have to get something like a boat or something out there 3.5 kilometers, and a laser on a boat is a bit I don't get that.
What is your point with that? That was Esteban, wasn't it?
Well, no, it was Crow that was just saying that. He was just
No, I
saying, well,
think
how
it's
would you
re-
measure long distance? Because Esteban was talking about why can't we use
I don't
a
know
small
what
one?
his point is with asking what do you do to make a bridge. Like, do you use a laser? Yeah, they might use a laser, but that would be them agreeing that the laser is going to give them the measurement that they need, and that's fine for two people or two groups or even a whole bunch of people. If they all agree that that laser is what they're going to use as a standard, that's fine. There's nothing wrong with that. That's not the argument. The argument is just whether or not you get to decide something for other people as the standard, and you don't. That's not how it works. You either agree on the standard or you don't. Your conversation isn't going to be helpful.
What do you mean agree with the standard?
No, not
What
agree
you
with the
elaborate?
standard. Agree on a standard.
What with the standard is meters and kilometers.
That's a standard. That's a
Okay.
standard of measurement.
Yeah, okay. If in the USA, it
Okay,
would
but
be
here, I'll
miles
give you
and
an
inches.
example to try and help you understand what I'm talking about. Okay, if I went and got a book out of my living room right now, okay, and I opened it up to page whatever, and that book said the Earth is flat. Okay, and I said, see, it's right here in this book. This book has the authority that an expert wrote this book. Says the Earth is flat. It's flat. Would you accept that as proof the Earth is flat?
No.
Okay, because you don't agree with my standard, do you? The standard that I just presented you of a book written by an expert, that's not a standard you agree with, right? So our conversation isn't going to be very helpful, if at all, because you don't agree with the standard I've presented. And I don't get to tell you you have to accept my standard simply because I said it is the standard. I would have to prove to you I would have to give you a good enough reason to believe the guy who wrote the book. Prove to you my standard. So in the case of measurement, you don't get to just pick an item or a tool or a thing and say this is the standard and then enforce it on everybody else. You have to prove to us that that is a standard that we should be willing to rely on. You have not done that.
Well, I think you reversed the whole thing because you were trying to force me, and not you personally, but the flat earth side was trying to force me to accept only the standard of physical measurement. I didn't accept that. I said there's other way to measure.
No, that's not trying to get you to accept it as standard. That's trying to get you to accept logic. You can't measure something unphysically. A measurement requires physical interaction. That's what a measurement is. It's part of the definition or the core being of the concept of measuring something is a physical interaction. If you are describing anything that doesn't involve a physical interaction, you're not describing a measurement, you're describing something else. Well, that's not a matter of getting you to accept the standard. That's just accepting logic.
No, I think I have a broad acceptance of standards while you focus on only one and not accepting the other and not even wanting to investigate it.
Whoa. What standard are we not accepting and what standard are we not investigating? Can you get a little more specific on that, please?
Using geometry.
Using geometry to
As
represent the visual,
what?
the way we see the world visually. Is that what you're saying?
No, measuring distance using trigonometry or triangulation.
Geometry isn't used to measure, it's used to calculate.
Okay, so you want to use the term calculate instead of measure? Okay.
No. I don't want to use the term calculate instead of measure. Calculating is different than measuring. That is just reality. That's just true. That's not me wanting to switch words. Measuring is not calculating. Calculating is not measuring. Those are two different things.
Hold on. Crow, you just said using trigonometry to measure a distance. That was the point I was getting to when I was saying if I wanted to measure how far this road is at this vanishing point, what angle would I get with the sextant? I would get 0 degrees. So tell me what triangle is going to represent that distance for me when I draw it out on a piece of paper.
Okay, well, measuring distance on the horizon it's known to be infinity, but let's talk about the tree, the third tree.
No, let's talk about the road. Let's talk about the end of the road here that I can see. That's not where the road ends. It keeps going.
Well, this is a drawing. So according to that drawing, it's at infinity.
Do you want me to bring up a railroad picture? Obviously, the railroad would go back. Let's just say that this is the railroad right here, okay? So I'm going to get a triangle that says 0 for here and everywhere past that, right? So how can I use trigonometry to measure anything past this point or down here?
You pick the point that you want.
Okay, I want that point right there at the vanishing point right there.
I see only the road with the trees.
Brandon, you should just jump into his world and do the field artillery. You know, just it's the same thing, man. Crow, put yourself out on the field. You've got a target out on the horizon. Trigonometry that.
Yeah, okay. So you measure the azimuth to the target. You move a specific distance to the side. You measure the angle again. You get a difference. You do the triangulation. That's it. So let's say that the difference of azimuth was 1 degree, and you move 10 feet. Now, Brandon, I've seen you've been using some kind of trigonometry site. You can put that, and you just get the distance.
All right. But obviously, I can't really use it to measure this end of this point. Trigonometry is completely useless for that. Can we agree on that?
Oh, it's a drawing.
Oh, do I really need to bring up a real picture of a road? When we know that this is how we see, right?
Yeah, and the real picture is that road is going to be up and down. Well, I don't think it would matter, but yes, but you have to move physically to produce parallax to get an angle to do the triangulation.
How are you going to triangulate something that's at a point right here? If I move over here, it's still going to be at this point.
Then it will be too far.
So it's too
Out
far to
of your
triangulate at that
range.
point. So there's a limit to how far we can use trigonometry to triangulate things.
No, I didn't say too far to triangulate. I said the distance would be too far.
Too far for what?
It's very long.
For what? Why is it too? What do you mean too far? Too far for what?
If you didn't get parallax, it means the distance humongous.
So I couldn't use that method to triangulate it.
Yeah, there's a limit. Yes, it's called the Bayes error. If you will move 1 feet, you will not get enough parallax. You have to have a good ratio between the side movement and the target distance.
What's a good ratio? What's that look like?
The perfect ratio, it's 1 to 1.
Okay. Okay, so I don't know if anybody else is at this point right now. This is too abstract.
Yeah.
What you're describing now is a complete abstraction. We have nothing to look at what you're saying. You just said 1 to 1. Okay, I don't know. You're proving our point, Crow. You're proving our point, man.
I say that's the best ratio. The less distance you walk, the more error you got. Combined with the accuracy of your compass.
Listen to yourself. Brandon just asked you that if the distance is too great, you're going to lose your accuracy, and you're confirming that. Yes.
Yes. Yes.
Okay. The fact that you can't see what you should see right now boggles my mind.
Yeah, I don't know how you can't see that that's a problem, that there's a difference between what you're visually seeing and your ability to write it on a 2D piece of paper if that's the case. There's a difference. If there's a limit to how far you can triangulate something because it's in the vanishing point or it's on the horizon, then you can't do that for all distances or all objects or all angles.
That's correct.
Because that's not reality.
No, it's not reality.
No.
Because there's the error for your compass. The longer the distance and the less distance you move to the side, that error is like.
How much is that error when we're talking about something that's 323 light years away or whatever? I mean, don't even answer that. Don't even answer it.
Yeah.
Don't even answer it.
I don't like this. I don't like this thing. Yeah. It's accuracy beyond my.
That's an arc micro radian.
Yeah, right.
Yes, something.
All right, let me get these out of the way. Do some show business here. Anthony Sicante. I read his last one twice, and he says 2 reads. Here's another super chat. Great show, guys. Keep it up. Flat Earth Cosmologies, Yin and Yang. What's up? Train tracks are level, so wouldn't that mean eventually you would go through the Earth if it's pear or ball, NASA? Esteban Ilabaca. This question is directed at Gleam. What kinds of measurements are used in the papers you continuously quote, direct or indirect? Please explain if those are all valid or not.
Well, the papers I continuously quote are globe papers. But anyway, yeah, if you're talking the likes of galaxies, then you're talking indirect. If you're talking the likes of plane surveying, indirect. If you're talking the likes of quantum, indirect. And they're what current physics are saying. And yeah, they're currently saying gravity is wrong. And do you agree with them, Esther? Put it up in the chat, meow mucker.
All right. The saga continues. Okay, cool. So, does anybody have any ideas for a experiment that we could do to kind of work out some of the questions here, that we could agree to some kind of methodology with Crow that would prove one way or the other whether, well, I mean, each of us probably thinks it's already proven, but one way or the other that visual measurements, angular measurements, are not the same as this 2D representation of reality.
Right.
Yeah, give me the angles. Go ahead.
Go ahead. What we would have to do, again, is what I've said from the beginning. He and I would have to go out on the field. He does his angular calculations, and I do my physical measurement, and we see who's more accurate. I mean, that's the way it is.
I was going to tell him to build. I was going to tell him to measure the angles on a Penrose staircase, and let's figure out those angles.
He's already admitted there's limits. So that's basically it.
Yeah, he has said there's limits. Okay. All right.
See, how I understand it is they'd measure the building, let's say, and you go up to the top corner, or even all corners, as more data points, the better. And then you would move to the left, and then you would take those angles again, but that would be at a known distance.
Yes.
That you could look up on Google Earth or something. But that would be the building in front of you in the foreground, not the background.
You know, someone can do this in his backyard with a compass, even the compass in iPhone or something like that.
Esteban Ilabaca with CLP 1000, are indirect measurements valid? He didn't get an answer.
No, the actual thing was they are current, or what measurements are possible with current theories of physics. Put it this way, no measurement is accurate at all perfectly. Whether direct. Well, you could say that 1 centimeter is 1 centimeter, but you could go down to the fractional hairs and stuff like that. But without splitting hairs, no indirect measurement is certainly accurate, 100% accurate. There is always error deviation, or always open to question. There we go.
And especially when the distances are so far that they can never be validated. So when you're measuring the stars, how can you even validate the distance that you're assigning to things?
Yeah,
you have several independent ways of doing it, and they all agree.
You cross your eyes.
Several indirect ways of doing it, right?
Independent.
He said independent, but I think he meant indirect.
No, I meant independent. I mean, there are ways you seem to be struggling with triangulation in this. I mean, Crow's trying to explain to you how you work out the distance to things using triangulation, and you don't seem to know how triangulation works. Something that's used by surveyors every day.
I think that was addressed earlier, actually.
Yeah, we already got through that. He's already admitted that there is a margin of error when it comes to that.
His first sentence stated that we didn't understand. I just want to point that out.
Rumpus,
we don't understand.
Rumpus, why don't you explain how we get an angle? We triangulate something when we're on a curved surface.
Well, that's when you get into geodetics. I mean, if you're just prepared to, if you're just measuring something that's over a few hundred meters or something, or even just a mile or so, you can do a reasonably good job just using planar techniques. Certainly the distance, you can certainly, it's not a problem when working out distance to things. For instance, if you wanted to work out something was 10 miles away, you could, you only have to move as Crow said, you just need to move left and right. And this is how, for instance, battleships and things in the First, Second World War used to work out the distance things, just using 2 points of, 2 optical things about, I don't know, about 2 or 3 meters apart, a rangefinder, and then using the principle of triangulation, you can then work out how far an object is away. And the curvature, the curvature doesn't come into this when you use that technique. To work out distances to things, you don't have to worry about curvature, providing you know that the distance between the 2 points is a straight line, which you can do with a rangefinder and with triangulation. And if you want to do this on the ground, I mean, over a few hundred meters, if you decide to do your triangulation by saying, I'll take point A and then point B, sort of a couple hundred meters apart, they are going to be level. There's going to be no effectively horizontal because the curvature of the Earth over a distance of 100 meters or so is negligible. So you can then use that and to work out the angles from that to your target, so that those buildings in the distance you had in your thingy there, your picture, good picture by whoever drew that, by the way. You can easily work out the distance things using a triangulation technique.
So you're talking about stuff over a couple hundred meters or whatever, which you would have to know the distance to that object to know whether you'd need to take curvature into account at all. You said use a rangefinder, but what about when we're talking about something that's 50, 100 miles away?
No, you wouldn't.
You said that.
No, you misunderstood. Here we go. Let's try it again. If you, over a distance of a couple hundred meters, you can use that as your baseline, the triangulation baseline. And over that, you can measure the angle to something quite a long way into the distance, over a distance of a couple hundred meters. You can probably accurately get a distance, I suspect, a good number of tens of miles with that. I mean, even over, if you had a good couple hundred meters, you could work out the distance something, I think, in multiple tens of miles away.
Have you done that before?
We work out the distance of things of the stars. We use the same principle of triangulation to work out the distance to the nearby stars. So one's up to about, I can't remember how many, like there's a few tens of light years. You can work out the distance them using just simple triangulation techniques, because the Earth orbits the Sun, and the distance between one side of the Earth's orbit is 180 million miles from one side point to another. So that gives you quite a wide triangulation base, and from that you can work out the distance of stars. I can't remember how many tens.
Where was the first value ever derived for the distance to any particular celestial object?
Any celestial object, but the moon obviously was determined.
No, the first one. Where was the first derivation of distance to a celestial object? When did that happen?
You're calling the moon a celestial object?
Are you okay?
Oh,
there's no reason.
Are you calling the moon a celestial object?
No. Hold on, Rumpus. Hold on. I asked you a question. I
need to know what you mean by celestial. I'm offering, is the moon a celestial object? And I'll tell you about getting the distance to the moon.
Okay, Rumpus, listen to my question again.
Yeah, you said celestial. I'm asking you to define celestial. Do you include the moon as celestial?
Rumpus, it's not very difficult. You're
I know. For you to define what celestial means.
You're a very sharp person.
Calm down, Rumpus. Let him get his question out.
I'm asking a simple question. He's dodging it. It's most annoying.
I'm going to restate my question, Rumpus.
You're going to have to define what celestial means.
Okay. The very first distance derived of any celestial object. You fucking choose.
That includes the moon then, doesn't it?
I said the first.
Right, but does that include the moon as a celestial object? So
is it the first one? Is it the first one?
But if you don't include the moon, then it isn't, is it, you twat?
Oh my fucking God.
If you're including the moon as an object, as a celestial object, then we can start talking about the first...
Well, this should be easy. Rumpus, is the moon a celestial object or not?
Sorry, I believe the moon's a celestial object. I'm wondering if he does.
So answer according to what you think. He wasn't asking somebody else what they think.
Well, I know, but I want, because I know he's an idiot, I'm asking to make sure we all agree that the moon is a celestial object. That's all I was trying to get out of him, but he wouldn't answer, that twat.
Rumpus, your mic sounds like shit. Are you talking through a wall or something?
Sorry, it is crap. Sorry about that.
He doesn't need to accept that the moon is a celestial object for you to answer according to what you think. He asked you about the first celestial object, so whatever you think that is, you can just tell him.
Misdirection, Rumpus. Listen,
we have
very
to.
hard.
Yeah, why couldn't you just said yes? I agree. A moon is a celestial object. Then I can start talking about that.
Because you're an imbecile. You're an
imbecile. You wouldn't answer the question because you didn't like it.
My question was
it was quite a reasonable question. You chose to dodge it.
No, the very first distance derived of any object in the sky.
Right, okay, that includes the moon, so I can start talking about the moon then. Right, so we're talking about, I can include, I believe, the most reasonable celestial object being the moon, and it's the nearest one. I don't happen to actually know when we use the triangulation techniques to determine the distance to the moon, but I suspect it was quite a long time ago, because it's very easy to do once you've got the radius of the Earth, which we have had for 2,000 odd years.
Okay, great. Okay, no. Okay, now great. How was the radius of the Earth determined?
Well, you can do it. Well, you could use the technique we've been talking about here, the Polaris one, for a start, knowing that if you can move up 69 miles.
Rumpus, are you a dumb fuck?
No, you
I
are.
asked you about the sky. You took me to the radius. I asked you about the radius. You took me back to the fucking sky.
Yeah, because you don't seem to understand there's an order to this. First of all, you can establish what the radius of the Earth is. Pretty easy to do. That's we've known that for many hundreds of years.
No. Don't tell me
having
your
established
fucking
that-
narrative.
So having
Rumpus.
established that,
How
you can then.
did you determine? Since you don't want to talk about determining the distance of a
I'm
celestial
perfectly happy
object,
to. I'm perfectly happy to, but you then ask me a subsequent question, then
I
sabotage
asked you
my
a
explanation.
subsequent question
Yeah, you
because
did, yeah.
you
So you
made
didn't let me
a
finish my
subsequent
explanation.
claim.
You didn't let me finish the answer to your
You
question.
made a new
You then
claim.
insisted on answering a new question while I was in the middle of answering your first one.
Rumpus, listen very carefully. When I ask you a question and then you give me an answer that makes a claim upon which your answer depends, I then have to have you justify your new fucking claim.
Yeah, without me finishing the process by which the first answer, and I'm happy to justify all the premises, but you can't stop. Well, you can, I suppose.
Which
but if you're
one
going
do
to
you
interrupt me on all the
want to
premises,
justify? Which one are you
right,
going to justify?
so you're not going to let me answer the first question until I've then provided the premises for my answer. Okay.
Can I just interject to move everything along? Both
Yeah,
the
go
sun
ahead,
and the moon was measured first by Aristarchus. No shit.
Yeah, I'm not sure. Yeah, the distance of the sun, though, he was very dodgy. I don't know when the distance of the moon was first established, but it's a
270
pretty.
BC.
Oh, okay, all right. So the distance of the moon, was it reasonably accurate?
Aristarchus, come on.
Was it done?
You should know.
I know
It was
that
done during the duration of the lunar eclipse.
Rumpus, this is absolutely. I'm incredulous right now. Okay, listen to me again.
Stupid. You don't understand.
When was the first?
I don't know, you twat, for absolutely sure, you moron.
I just said Aristarchus.
Rumpus.
Apparently, according to Cleans the Reflector, I could Google it. I don't know when the first observation of the distance of the moon was, but I suspect.
Well, then how
Rumpus, please don't scream into your mic.
How can you make any claims about distance
he's such
and
an annoying
parallax?
twat, this guy.
How
Right.
can
So
you
when
make any...
when does this end?
Right, so let's first of all, as I suspected it was the Greeks, because it is once you've got an idea of the radius of the Earth, which obviously the Greeks had, they knew what the radius was within a reasonable within 10%.
Oh my God!
Better than that. So once you've got that, it's quite easy to do triangulation mess. I mean, in fact, you probably don't even need. You might. I don't know what the distance of the moon. You might even
somebody
be able
kick
to.
this guy. Why can't we kick people anymore?
You're a moron.
Somebody kick this guy.
You can't even understand basic geometry.
I'm waiting for an answer, Rumpus. I haven't heard you answer a simple fucking question.
This moron is interrupting me every 5 words.
All right. Oh, nobody interrupt him. Give us the answer now, Rumpus.
It keeps on interrupting.
No one's interrupting you now. Give us the answer.
Okay, all right. So you are. Right, so I don't happen to know. Gleam says it's the Greeks. I'm perfectly happy to believe that, because all you need to do is the same triangulation technique that I just described earlier and Crow's described, of just moving a few miles, and then you can triangulate on the moon. And that's relatively easy to do. You only need a few tens of miles to do that. So I don't happen to know when they did it. Gleam says it's the Greeks. I'm perfectly happy to believe that's when it happened, to a reasonable accuracy. But I suspect historically we don't know absolutely for sure for Mr. Moron Aetherband, when that actually happened. I suspect it happened several times, but we're not
Everybody drink.
History. Yeah. So anyway, so why he's interested in the first date of this, I do not know. But anyway, we know it must be at least done reasonably accurately within sort of 1600. That's for sure. So that's gonna. So what? But obviously,
you don't know. You don't know anything. You haven't given us an answer yet. So I'm going to interrupt you. You haven't given us a fucking answer.
I don't happen to know the historical facts.
Get off the panel, Rumpus. Get off
You're
the
a moron.
panel.
Just because I don't happen to know the historical date of the distance to the moon is just a ridiculous point. Why does that matter? Why is that relevant to anything?
I'm going to ask you to verify how you know the distance.
Well, how we know it currently is accurately.
No,
I didn't Yes. That's how we know. Yes, you moron. That's exactly how we know how far the moon is away. Exactly.
Was not about the current. My question was about
okay, so we don't know when the first was done. So what? Who cares when it's first done? Doesn't matter.
Okay, great. How do they do it now then?
Right, they use it by bouncing lasers off the moon.
Bouncing lasers off the moon.
Yes, bouncing lasers off the moon. There's a whole bit of, I can't remember who, it's not a NASA site, but it's a very large and powerful laser that sends off lights onto the reflectors put there by Apollo astronauts.
We all know the story.
And
we all know the story.
good. Well, apparently he doesn't. He didn't
Yeah,
know this.
I
apparently.
do, Rumpus. Yeah.
Well, then why do you say that? Sort of, oh, do we do this then? So if you know the answer, then why?
How did they validate the distance that the lasers gave them?
Well, we know the distance from other techniques.
Of course. So you already knew it was a globe, and you already knew how far the moon was. So the lasers had nothing to fucking do with it.
Well, they do. They make it more accurate. They do it within a centimeter. They have an accuracy of better than a centimeter. Whereas the other techniques are not quite as good as that. So we use the laser.
Rumpus. So Rumpus. Okay, so listen. Let's just say for shits and giggles, because you don't know the very first calculation. Okay, so let's just say back in 675, someone estimated that the moon was 238,000 miles away. Okay.
We don't estimate. Well, okay.
Will you hold on, please?
Makes that like a guess.
Please hold on. Please hold on. Okay. I'm being a little bit general. Okay. So just cut me a little bit of slack of creativity. Okay. Okay. So when we get to the point of having lasers and we think, hey, let's shoot a laser at the moon and see how long it takes to get a return. If you already have a predetermined distance and you shoot the laser and get a return, then all you're doing is doing the same thing that I said before about predetermining the circumference and then dividing it into 360 degrees. Okay, you haven't measured anything.
Gibberish, utter gibberish. Of course you've measured something. Just because you happen to know a good idea of the answer beforehand doesn't invalidate the measurement, you moron.
Hold on.
Jesus Christ.
What was the measurement, Rumpus? What was the measurement?
What was the measurement of the laser? What? Sorry, the recurrent one?
No, just that you said when you make a measurement, you have an accurate measurement. What was the measurement made? With the laser, right? What was the measurement? Did they measure distance or time?
Well, they measured time.
Exactly.
How is it that we can accurately measure with a laser to the moon? How is it that we can accurately measure using a laser to the moon, but the limit on Earth is
simple formula to convert
a few hundred
time
meters
into distance? My God, how can you? If you think you've made a point, you are an utter moron. There's a very simple formula relating time to distance if you know the velocity of the thing that's going up there. So we know the velocity of the speed of light very, very accurately. Therefore, we know the time taken to get back. Therefore, we can work out the distance using a very, very simple formula.
And you just assume the medium in between. Yeah.
Well, when you... Yeah, well, the fact that some atmosphere only slows down the light very, very slightly, and because you're pointing up through the light, through the atmosphere, you're only going few of... with the denser part of the atmosphere is very little. So
and conveniently, in between, you just have space, so it doesn't get in the way of your mathematics.
But they do allow for it. But you have to make some estimates. But the correction is very small. So what was your point? Sorry, say again. What was it? You made another point, Brandon.
Yeah. So my point was, how can you measure with a laser to the centimeter, to the moon, but the range for measuring with a laser on Earth is only a few hundred meters?
Well, the laser used to measure the moon is a very, very powerful laser. So I think if we were to use a laser in the atmosphere using high-powered ones, then I think you could get some accuracy. I presume you're referring
just say super duper laser.
You're just referring to the sort of lasers that are stuck on theodolites, which are, I don't know how accurate they are.
But it's not few meters, it's few kilometers.
Okay, few kilometers versus 240,000 kilometers.
Yeah, that's too much.
The amount of equipment. I mean, if you've seen the laser thing, which
just say super duper one time for me, please.
If the equipment used to determine the distance to the moon is a very, very powerful laser, an incredibly expensive thing that can't move. So it's not the sort of thing you can set up somewhere and then measure it.
So you need a super duper laser to do this.
Is it the James Bond one?
You need a powerful laser indeed to go to the moon and come back again, because I can't remember how many. I think they only get something like 5% or something return, or is it 10%? Something like 5 or 10% of the thing, the laser beam, the laser shots they make. They only get 5 or 10%.
Nah,
back.
just make up
They're
a
getting
number. It doesn't really
photons
matter.
back, Rumpus. Why are you lying? They're getting photons back out of trillions. This
Yes.
super duper laser they got is getting a couple photons back.
Well, it's about it's 5 to 10%, something like that. It's a low percentage of the photons they fire out they get back. Is that the point you arguing with me over this?
Say super duper once and I'll let it go.
So it's the moon is not very reflective, and obviously you need a. And I think by the time the laser gets to the moon, I think it's. I can't remember how many tens of meters it is wide, but the beam has diverged quite a bit. So the actual bit that hits the reflector, and the reflector's only, what's it, meter by meter or something like that. The actual bit that hits the reflector is very small, and then it's got to make its way back.
Who cleans the reflector?
Sorry?
Who cleans the reflector?
Well, fortunately, there isn't any mucky wind on the moon, so you don't have to worry about that sort of thing.
I'm joking. I thought it had been dusted over a long time ago. I thought you couldn't even use it anymore.
You don't even need the.
I think one of the reflectors is not working terribly well now, but I think there are 2 or 3 sets down there, and one of the sets is working perfectly. I think one of them may have been affected by something, possibly. When the moon's always being hit by meteorites, and perhaps a bit of dust was kicked up and got over it. But one of them is definitely working perfectly. One of them is.
That's why we need to get back to the moon to clean the reflectors.
Yeah. What is it now? 2030, 2035? What are they saying now?
Well, we in the 60s, the US was spending 5% of the GDP of the country on that exercise.
What's your point? What year are they going back?
Well, it's going to be dependent on how much money the US government is prepared to pay, basically.
You guys are really tempering the expectations lately. Before it was, wait till we get back to the moon in 2024, shoving that down our throats every day. Now it's, well, if we have the money and Congress and...
Well, of course it is. You don't think it costs money then? You don't really... That's why I pointed out the enormous expense it is to do that operation. That's why I pointed out the 5%. That's, for instance, that's bigger as a proportion of GDP. For instance, that's something like twice the size that we spend on defense.
Well, it shouldn't be that much this time. We've got much better technology. We're much smarter, much more technologically advanced. Should be a piece of cake.
No, it's not, because getting off the Earth and firing up, you can't, at the moment, we still use chemical rockets. So basically, you have to build something as big as Saturn V still. The technology for firing the rockets up hasn't changed. It's still a matter of having oxygen oxidizing kerosene or paraffin. So that hasn't changed. We have not got a new chemical reaction to give us any more power. So we still have to build something the size of the Apollo. We haven't got anything better shoving technology at the moment. So that's still going to be a big object. And there's no fixing that. There's been no improvement to that. Even though we can have better computers that are smaller, and we can do all sorts of clever things, and we can use better materials that are slightly lighter, and God knows what. But the fundamentals of it, the amount of fuel you need to stick in there, is still about the same. And so unfortunately, you still need to build something the size of Saturn V, and that's a big thing. Now, obviously, perhaps the cost of all the monitoring in the Houston, whatever it is, mission thing might be smaller.
Let's get out of fantasy land.
But the rocket side of it is not going to be much different, unfortunately.
Don't you lot remember the YouTube ad? It's the rocket equation.
I don't know why you're obsessed with the fact that this is a political decision about whether going to the moon or not, and so it's subject to what the government does. If the government gives them 5% of the GDP again, they could be there in a couple of years, no doubt. But if they only give them whatever the fraction of NASA gets to the GDP at the moment, they're going to be there. It's going to take much longer.
So they need let's see, the budget is, what is it, $3 trillion a year? So you're saying they need $150 billion to build that rocket and get everything going?
I don't think it's $3 trillion. That would be, I don't know. I think you're getting overexcited there.
No, I'm pretty sure
just spent
it's up there.
We're about 20 trillion in debt, so I mean 3 trillion's like nothing.
Yeah, that's like pocket change. You do realize that we could print as much money as we wanted. We just printed like $7 trillion because of this medical emergency.
You just claimed it was 1 trillion overall. How many trillion did you say it was?
I said 3. I'm not sure, but I think it is something like 3.
So 3 trillion. Do you know how much it actually is?
How much?
22 billion. You're a factor of 1,000.
22 billion is the U.S. annual budget?
Yeah,
No.
for NASA.
No, not
Yes.
NASA.
Oh,
I'm
for
talking
NASA.
about
No,
the U.S.
we weren't talking
annual
about-
budget, Rumpus.
Total.
Oh,
Total
it's NASA's budget.
Rumpus.
And it's currently
Yeah, come on, it's 20 bills.
0.4. Hold on, it's 0.48% of all U.S. government spending. So it's a factor of 100 less than it was in the 60s as a proportion of GDP.
Not 0.48 times
It's
10
one-
is
it's
what?
It's 1%.
Not 0.48%.
Sorry, 10%. Sorry, I get myself
10
excited
times.
now.
10 times.
Yes, 10. Yes, it
10
says 10
okay.
times. It's 1/10
All right.
of your GDP you're spending now as you did in the 60s in the US.
That's pocket change, Rumpus. If we wanted to do it, we could do it. I think there's
Yeah,
probably
exactly.
another reason we don't do it.
No.
Yeah.
If the US wanted to spend 10 times as much on NASA, they would be able to deliver this no problem. But if you have this 1/10 of what it was, then having, they can't do it. Well, it's going to take a lot more.
Well, obviously they're not serious about doing it in 2024 if they haven't already increased the budget, right?
No, they're not serious. No, they're not serious about doing it in 2024. The government is not serious about doing it about that. No.
Surely,
okay.
if it's that amount of percent for about 8 years, surely, I mean, we've been what 40, 50 years now.
Yeah.
Yeah, if it was drip fed.
Well, yeah, but they've been doing other things. They haven't been spending all this.
Yeah, watering.
You are aware they've been doing other things. I mean, they've had the shuttle, for instance. I mean, what a
Parker
stupid
Solar
question.
Probe, $5 billion.
So,
Do you know how many
you don't
times they
think-
grew lettuce
you
and
think-
potatoes
you
in
think
ISS?
They've been doing nothing. They've been saving all the money year on year.
No, but what they could have done, Rumpus, is made a bigger Solar Parker probe, go up there, right, and then fire the Solar Parker probe off of the moon, but while having men on it. Why not do that? Why
Because
spend
it
a
costs
quick
a lot more. They didn't have the budget for that.
But
It's quite
what's
simple.
so urgent about sorting out the sun now instead of just putting that
Well,
$5 billion in a piggy bank?
It costs a lot less to do that than it does.
A
to
Mars
build on a moon mission.
helicopter, Gleam.
My God, I don't know. How,
Mars helicopter, important technology, bro.
Well, how much do you think the Mars drone cost then, Montreal?
I have
$80
no
million,
idea.
Rumpus. 80 million, I heard.
It's comical, Rumpus. Come on, get off
Well,
of
you're
it, bro.
comical if you think that is somehow going to impact on the budget to the moon. If you think it's a substantial fraction, it's going to impact on the budget, the possibility of getting to the moon because they're building a Mars helicopter. My
if
God.
they were serious
So
about doing it, you would
2014
think they
we're
would
on the
increase
moon,
the
Rumpus?
budget now to go in 2030. I mean, 2024 or 2025 is out the window completely at this point. If they want to get there, they better start ramping things up right now, right, Rumpus? How long did it take us last time? Like 9 years to build everything up? 10 years?
Yeah.
So we're looking at 2030 at the earliest at this point, probably.
Well, it depends on what the government decides to give to NASA.
Sure. Why are they going around telling everybody that they're going to go to the moon then?
Well, as an objective and as an ambition. I mean, if a president came, I mean, old Kennedy said, was it 61 or 63? I can't remember now. Was 61? The ambition to go to the moon before the end of the decade. Well, that was a mission. That was an ambition that was firmly set down, and then governments, and of course it was all in the Cold War, so that every government subsequent to that and every president subsequent to him was keen on supporting that.
Oh, they had other motives at that time.
And they were going to make it
They were
happen.
motivated in other ways, is that what you're saying?
Oh yeah, well they felt the Russians were going to get there, so they decided to spend 5% of their GDP on NASA, which they're not prepared to do at the moment. They don't regard as a race to the moon like they did in the 60s.
So it's probably more important. The non-science part was probably the most important part back in the 60s, the most important motivator, right? I mean, the science part is still there, but that's what really got them to do it, was to beat the Russians and win the Cold War. They had a huge motive.
Yes, that's what that was the motive of the politicians to give NASA the money. Obviously, NASA wanted to do it. I mean, oh God, who's the German? The guy who was in charge of NASA at the time. He was had a lifetime ambition.
But they probably would have done anything to get that mission.
You don't really know much,
done
do you,
in the
Robert?
60s, wouldn't they?
Well, I'm busy trying to deal with lots of idiots, and I can't. I've got multiple threads going in my brain.
Come on, Pete Shay's taught you all about Aristarchus. Haven't you been listening?
No,
if we got time, I'd love to go over some Foucault pendulum thing with Rumpus.
You know what?
No
I think
one
that's a
objects.
great idea, Jeremy. I think we beat the moon mission to death. We figured out we've got at least 10 years to wait, and we'll see what happens after that. But Jeremy, why don't you bring that up? Rumpus, do you mind answering some questions from Jeremy?
No, not at all.
All right, go ahead.
Sure. So, would you say that the Foucault pendulum, the precession we see in the pendulum, would you say that's due to the deviation from the Coriolis effect?
Yes.
Yeah. And does the Coriolis effect, would you get a different deviation if you're going north-south as to say east-west?
What's going northeast or southwest? What are you talking?
If something's going north-south, right, or east-west, will you get the same deviation for both of those directions, or is it different?
It is actually the same. The Coriolis force causes things to. Well, it depends which half of the hemisphere you're in. One will cause it to rotate one way, and one will cause it to rotate the other. But it's actually the same, whichever direction you actually point in. You actually when you're at the equator, the Coriolis force effectively forces things upwards. If you're going east, west, and north, south. So it's only the Coriolis force actually only becomes important in terms of horizontal forces when you're sort of mid latitudes.
So you're saying the deviation is the same if you're going east, you know, if you're in England and you're going east west, you get the same deviation as you would north south, the same amount.
Correct.
All right. I mean, that ain't what the other.
Yeah.
All right. Never mind.
It's
I guess there's nowhere to go after that.
It's quite complicated to work out why that's the case. The maths is quite complicated, but it is the same.
That ain't what. This is why
Can
they
I
don't
get a
fuck
question
with you.
in after Jeremy?
This is why they don't fuck with you in gems, bro. All right.
Go ahead, Montreal.
Rumpus, you said that there's deviation due to the Coriolis, right?
Mm-hmm.
What force is acting upon? Let's say we're on a merry-go-round and I throw a ball, right? What force is acting upon that ball?
From our reference
to cause
frame,
it the deviation.
From our reference frame, in a rotating reference frame, the Coriolis force is what's called an inertial force, a fictitious force, and a apparent force. It only exists as a result of being in our reference frame. So we only see it from our rotating reference frame. But it is as much as a force as I think. I don't know whether you were there when I showed a video. There's a video I've got that I think might be illustrative to people. I might just.
I was there and we were discussing how the room is rotating, if I remember correctly.
Okay, well, let me show other people. You might have been there, but other people weren't. So let me just show them, given that they'd all bring them all up to speed. It'll only take a few seconds.
I mean, your boy Xanax got a different opinion on that than you. You guys got to get your story straight about the amount of deviate. That's your boy, right?
Well, we don't always agree. I think he's. He. Let me just hold on. Let me just see if I can find this thing. Here we go.
That's great.
Okay, let me. I'll just hold on. I'll deal with that in a second. Let me just show you this video that you may the Montreal has seen, but other people may not have done.
I mean, what kind of deviation we? Oh, go ahead. My bad.
Okay, let me just show this. Let me just show this video. So let me.
That would be 15-degree, Jeremy.
No, it's got nothing to do with that.
Oh, I moved my head.
You shouldn't move your head.
Do you get used to this?
Yeah, you get used to it. Yeah. You can adapt. Move your arms and try to feel this force that is.
Okay, just to be clear, I'm not putting this on. As far as I'm concerned, I'm the signals I'm giving to my muscles. I'll move my arms forward, and now I'm forcing them, but I'm pushing against a force here.
If you keep going,
basically that's what he said, Brian.
You won't feel the force.
Now he's going to argue against it.
Oh, that's weird.
That's weird, right?
That's so weird.
So now you are adapted.
I mean, I'd like
so
to
trying to do anything else, I haven't adjusted to it. But that specific movement, my body's got used to.
That's right.
Wow.
One way to visualize this force is for me to try and throw a little tennis ball at you. I will throw it straight at you and see what happens, okay?
Whoa!
Right, did you see that, or was that twat over talking? Hopefully you were ignoring the twat over talking.
Go ahead.
Right. Oh, good. Okay. Well, so hopefully what you saw there was a guy in a ball in a rotating room. They were on the inside of this room. It's like a merry-go-round, and then one guy threw a ball directly at the other, and the ball just seemed to whip away to the right, I think, of the guy. And
Seemed, right, Rumpus?
Well, it did. From their perspective, if you were to take the coordinates of the ball with reference from their reference frame, it moved physically.
With reference to their reference frame. But did the ball travel in a straight line, Rumpus, when released?
In their reference frame, it did not.
I didn't ask you that. I didn't ask you that.
Because everything, when you say does something travel in what, you have to say with regard to what reference frame. And in the reference frame of their room, it shot off to the right. And but the thing is, listen, the key point is, and that's what we're like on the Earth. We are in a rotating reference frame, so we see things shooting off like that, except not quite to that degree. So that's the view that we have on the surface of the Earth. From our point of view, the ball in that situation shoots off as though it's having a force acting on it. Now, you happen to know that if you then move outside into a different reference frame, let's say you're looking down from space, you can see that things travel in straight lines. But that's not the view that we have in reality.
So we got to get
nearly there. In reality, we are in that room. And we see things and measure things using, if you had a little laser measurement, for instance, in that room that was pointing at that ball, it would show that it shot off to the right as they saw it.
All right, so Rumpus, how high do we got? Hold on, Rumpus. How high do we got to get up to leave this to get into the other reference frame, the inertial one?
Yes,
how high
the
up?
One. Well,
how high up?
Well, you just have to be not moving with the Earth. So in theory, if you were able to hold yourself stationary, I mean, you could go into the center of the Earth. If you could somehow get into the center of the Earth, that's also stationary. But if you could somehow get away from the rotation of the Earth, you would see it immediately. So you don't,
how far away does it stop rotating?
Doesn't matter.
That's what he's asking you.
What's
rotating? What's the number? 10 miles?
If you can ignore, if you
Why
can
are you
screaming? Let me ask, because you're not letting me answer your question. It's not a matter of height. It's a matter of whether or not you move with the Earth. If you were able, friends, hold on. If you were able to get up, just jump up and then somehow fight the speed of the atmosphere and make yourself stationary in space, you'd have a bloody great gale blowing on you. You could do it then. You would see it.
But let's say you're Superman. How high would you have to be to reach the Lagrange point, for example?
Lagrange was have nothing to do with this. So
or the point you get the Lagrange. Let's say the point where the atmosphere stops spinning and we reach space. What point is that?
Hold on a second.
To do with this.
Why are you over talking me, Rumpus?
Because you're bringing the Lagrange point.
You forget the Lagrange point. At what point does the atmosphere stop spinning?
Well, the atmosphere ceases to be much more of an atmosphere after about 60 kilometers, although the odd molecule shoots out further than that. So
let me just.
It depends whether you want to fight against the atmosphere or not. I mean, you could do it 1 inch if you wanted to above the ground, or you could in fact be on the ground if you're prepared to run.
Okay, you're beating around space. Where does space start? You're beating around the bush.
Hold on. Let me regarded as being at 100 kilometers. That's where it's regarded as being, even though Earth's atmosphere goes beyond that. Because it's a gradual thing. You've got to say, where do you pick on? I mean, you could argue if an Earth's molecule from the Earth's atmosphere made it all the way to the end of the universe, does that mean to say that Earth's atmosphere is all the way to the end of the universe? Well, you've got to decide to pick on somewhere. So the place we've picked on it is the fact that you've got called the Kármán line, which is where the lift of there's so little aerodynamic lift, you have to be going at orbital velocities to hold your elevation. That's the definition of the Kármán line. So
okay, one more question and then I'll give it to Jeremy, if he doesn't mind.
Go ahead.
Because you double spoke there, Rumpus, when you were showing the room. Now,
no, I didn't.
You equated the spinning Earth right away. You assume that. We'll put that to the side.
We know that for a fact.
You sure? You know that, but not us.
We can measure that very easily.
Right. Okay. Now, the spinning room. I want to make something perfectly clear. The ball appears to deviate. Appears only to the person in the spinning room. If you were to take a picture of the ball from an independent point on top, you would see the ball travel in a straight line.
Yeah, but if you took a photograph, as they're doing, but if you took a photograph with a camera in the room, it would move and it would appear to have a force acting on it.
On the rotating reference frame, correct?
Yes, on the rotating reference frame.
So it's a visual effect, correct?
No, it's not. It's a reference frame effect.
I give up. Go ahead, Jeremy.
Can you not see?
I'm done with him.
If you took the coordinates of that ball, if you decided to put a laser on it, or you put a grid on the floor of that room, you would see that it changed the coordinates in a curve.
We know the Coriolis effect is a real thing.
It's all about reference frames.
Yes, we know the Coriolis thing effect is a real thing. We know. Thanks. So what kind of deviation are we going to see when we're going east-west on the globe?
Well, it depends on your velocity. The Coriolis force is dependent on your velocity. If you travel very, very slowly, the force is very small. If you travel faster, the force is greater. If you know the formula for the Coriolis force, which I can show you if you want to, it's a function of the velocity of travel.
So the Earth spins under you at different speeds depending on how fast you're going?
I didn't say that, you moron. I said that the force that acts at right angles to your motion is dependent on your velocity. Yes.
Double
but the Foucault pendulum
the plane
does.
is a bit different because it's driven by engines, so it's constantly correcting its force. But if you fire an artillery shell, which doesn't have engines and doesn't have someone on board redirecting every few seconds, then it is subject to the Coriolis force, and that's why they had to make a correction for those things on battleships ever since the First World War, when they started firing over more than a few miles. Yes, they did. If you're just denying history now.
Absolute rubbish.
So you're denying then that on First World War battleships and Second World War battleships, they have got computers in them, or analog computers, that actually make corrections for Coriolis force. You're denying that, are you? Yeah, and include Coriolis. And they have to include a Coriolis force in that. Well, absolutely it is. We're just denying history. That's exactly what they did. That's exactly what they do. The firing table, indeed, the firing table that you're talking about has a Coriolis component in it. And if you're denying that, they did. They have to put in the computer, the firing table, which is effectively an analog. Well, the people who designed the firing table, the analog
Citation,
computer,
please.
has a factor in it for Coriolis. And if you're denying that, you're denying basic history. And it works. Yeah, and it has to include the Coriolis factor.
Got it.
Well, they include in the in the firing table. That's my point. They had to allow for the Coriolis.
Let me ask Rumpus something real quick. Hey, Rumpus.
That is how it's designed, and if they didn't allow for the Coriolis force, then the shells would not land accurately. They had to include it. They're not going to
Rumpus.
put it in just for giggles. They had to allow for it, and it's a fact that they did. And if you're denying that, you're denying basic. I know that they designed it with the Coriolis force in mind. You seem to be knowing.
Rumpus.
Measure it. You include in the calculations. You include in the calculations. Yes. In which you'll find there's a factor. There is a factor in that machine. If you've got the book, then you. Yes, I have. I'll go to it if you want. You want me to bring
Rumpus.
up these firing tables of Alpha Coriolis? Okay, I'll go. Yes, and which the gets to the shell, and the shell then gets on target. Without it, the shell doesn't get on target, which is a test of the existence of the Coriolis force.
Hey, well, let me ask you a question real quick.
Well, if you know what it is, and you design it into the machine. No, hold on. You're just in denial. You're just in denial.
Rumpus, does the speed of the
include a Coriolis component? If they didn't, the system wouldn't work. You're in denial of history if you're saying they didn't do it. Build in a Coriolis factor. You're in denial. You are denying what they did. Exactly, because you're not understanding it. Do you not understand that it's a test? If the designers of that firing table included a Coriolis factor to make it work, then you either deny that or accept it. Say it again, sorry, I missed the start of that sentence. Well, it's going to vary with each firing table. They're going to have a history of what the rounds do.
Boris Rumpus.
But for any particular firing table, I don't happen to know. The point is, you don't understand basic logic. You don't understand basic logic. The designers of that firing table, included Coriolis as a factor. And if you don't understand how devastating it is for you, they need to measure it, you twat. They included it. No, they don't. They knew that. Well, I can, because I can go to have the design of that table, and I can show you that they included a Coriolis factor, and then it had to. What do you mean? So what? The fact that of course they did. Yes, they did.
That's ridiculous.
How they do it, because what you have to do, it's a function of the longitude and latitude. It's a function of your velocity. So all the user of the table has to do is to punch in the latitude, longitude, and velocity, and the direction of your velocity. So that's what the user does. But the designers of the machine then say, knowing that, I'm going to feed that into my Coriolis calculator inside the machine, and out will pop an answer. And so you're basically denying what these designers had to do. They didn't just say, "Oh, look, we'll just take a number from shooting off shells in different directions, and then guess, and then try and sort of do a database of angles, and then say, okay, we'll remember what the database for this angle, and this velocity, and this latitude and longitude was, and then store that in the machine somehow." No. They made the calculation for Coriolis using a mathematical equation for it. They didn't remember previous shells going off. They had the calculation for it in the machine, fed in with all those three parameters.
All right. We got it. You're repeating yourself again. Brian, you had a point to make. Go ahead.
What happened?
Yeah, I wanted to ask a question. Hold on, Jim. Hey, it's Rumpus.
I've turned you down, so that's why I can't.
Yeah. Now check it out. It's the faster the projectile goes.
Jesus Christ, loud again.
Let me ask a question. Does the projectile experience more Coriolis if it's going faster?
You just said that. I know.
It's a function of velocity. Yes, the force on it is greater. Of course, the bigger the object, the extra force.
Guys, mute if you're not talking. We're getting some bad echo.
Yeah, someone's echoing. I think it's Brian. Yes, Brian, isn't it, as usual? So yes, as I can show you the formula for the Coriolis force if you like, and there's a factor in it of the velocity. So the more the velocity is, the more the Coriolis force.
So the Earth is spinning differently. If the bullet's going slow or fast, the Earth's spinning differently underneath it.
To get that to how on earth do you work them out from what I just said?
That's exactly what you just said.
I didn't. I mean,
The speed of the bullet is going to matter how much the Earth spins underneath the bullet. Apparently.
No. Oh my God! How stupid can you be? The Earth spinning is a constant. The velocity you're firing this thing is not a constant. The Coriolis force. Do you want me to go through? Do you want me to show you the equations?
No, we don't need to see the equations.
You're too stupid on it.
So if you fire a laser beam, if you fire a laser beam from north to south, does it curve?
And therefore, if it's a function of velocity, if you go faster, the Coriolis force is greater. It's a simple part of the equation.
Okay, let's say both bullets go 1 mile, right? Except one goes way faster, and the other one goes way slower. they're not going to land in the same spot because the Coriolis was different?
Correct.
You know how insane that sounds? Or is it just me?
Yeah, so Jeremy, so do this. Let's take a laser beam. Laser beam's going fast as we can do. So shine a laser beam north to south. Since it's going fast, it should get tons of Coriolis. It should be bent. It doesn't, you stupid dumbass.
Right, but when I said the force acting on it, you have to bear in then you're now talking about the actual deviation. So if the force is a function of velocity, but the time taken in the path is very small, then the force will have a minimal effect. So in fact, if you actually look at the thing, if you go fast as light, there is almost no effect. And if you go very slowly, there's almost no effect. If you go into an intermediate thing where you take a long time with a reasonable velocity like winds do, then you get something called the Rossley number, which actually tells you what the deviation, which is actually what you're more interested in. When you ask me about the force, actually,
so depending on your speed, hold on.
What you were more interested in, I think, was what is the deviation.
So any other speed except for what we could detect it with.
You've been talking about Coriolis effect this whole time. What were you talking about?
Hold on, but don't you do understand that if the force is greater with a greater velocity, but if the path time is very small, that force only acts for a short period of time. So
how about if that force is just visual, Rumpus, and it has no effect on anything? What then?
Again, so do you understand that if I have a large force but it's only acting for a short time, the deviation, which I think is actually what you're more interested in, is actually quite small.
You know that's what I was interested in, Rumpus. I asked you if the bullet was going to land in the same spot. What else would that be besides the deviation?
And it's not.
Why are you double talking yourself and shit? You're like running in circles.
The Coriolis force is quite a complicated concept, and you're not intelligent enough to understand it.
I asked you if the bullet was going to land in the same spot. You don't think I was talking about the deviation?
You were very, very clear about it, that it doesn't. If you have a bullet traveling at different velocities, it would land in a different place.
And that's not the deviation.
Not just.
It sounds like this force just acts unilaterally, Rumpus. Just acts when it wants to under certain conditions in different ways, depending on time, velocity,
depends how
weather,
or convenience.
Yeah, just how you talk to it. Faster in winter than summer.
You can sweep water all the way. Yeah.
Like it's
works
yeah,
in
it's like
mysterious
it's sentient.
ways.
It just makes its mind up how it wants to work on a certain day.
If you
Absolute
get Clean to sing to it, it's going to respond better. You know, things like that.
Deviation. I know you don't want to be faced with a bit of
Exactly,
science.
SE, exactly, mate.
You said a lot of crazy shit about Coriolis tonight, Rumpus. You need to go just relax and think about what you said.
Time of flight is critical.
Do you have any evidence of Coriolis actually being measured? Any experimental evidence whatsoever that we can see?
Oh, the focal pendulum is a measures Coriolis.
Earth-based Coriolis, not the Foucault pendulum. I want to see some actual Coriolis.
Well, that's what the focal pendulum is, Earth-based. What do you mean?
That's what you say it is. How do I know that it's some Coriolis force of the Earth spinning causing the pendulum to do that?
Yeah, the Foucault pendulum debunks Coriolis because it's not consistent.
If you think it, I mean, on a flat Earth not rotating, there would be no such thing, and there would be no deviation. The Foucault
Says
pendulum.
you.
So the fact we have.
Foucault pendulum goes whichever way it wants.
You don't understand the maths if you think that. Do you want me to get you clearly need to see this formula on the Coriolis force.
No, we don't.
Well, you don't want the maths, okay? But the point is, you would not get any deviation of a focal pendulum on a non-rotating Earth, and as you do get a deviation, therefore the Earth is rotating. You put it simply as that.
No.
That sounds like an FP then Q fallacy.
There are lots of other reasons why the Earth is rotating. For instance, if you have a gyroscope, as Bob Nodell discovered, you get a 15-degree rotation in an hour. You also, if you drop something vertically, it doesn't fall directly underneath it. It's actually affected by the change in velocity from the top and the bottom of So, for instance, if you're at the top of the Eiffel Tower and there was no wind and you dropped something, it would not land directly underneath where you dropped it. It would be deviated, it'd be flung further to the east.
Right-hand rule.
Except we never see that.
Of course we do. We can measure that. If you, for instance, if you go...
Hold on, hey, Rumpus, the interferometer, Bob knows...
I turned it down, Brown, because you shout so much.
Hold on, man, hold on.
Let me just finish up the tower. Someone said we don't see this, and we do. There's a tower in Germany that actually is designed, I think it's about 100 meters high, that's designed to have things dropping in it. And in using that tower, you can actually see the deviation caused by the difference in the velocity of the top of the tower to the bottom of the tower. So there's another proof that we're rotating, as well as gyroscopes, the focal pendulum, also the way we see the light, for instance, is redshifted in one direction and not in the other. Is one other reason. Then what's the other effects? So I've mentioned 4 anyway reasons why we know that the Earth is rotating.
So a bunch of effects that you have declared are tied to the rotation of the Earth.
God, they let me talk. I could
Go ahead, Brian. Brian, go ahead.
Okay. Look, he says that you got to be moving, and faster velocity, you get more Coriolis. Okay, the gyroscope, if it's just sitting there, it's not moving at all. Okay, and what?
That's not a Coriolis effect.
Yeah, we know it ain't. We know that Bob didn't prove the Earth's rotating because
the Coriolis force only occurs when you have a velocity with regard to the inertial reference frame. So that's the Coriolis force. But the rotation does other things, including what I just described about things do not drop vertically, and also the gyroscopes also show this, but that's not a Coriolis effect. Just because the Coriolis force is one way of measuring rotation doesn't mean to say there are not other ways of measuring rotation. So again, you're being stupid here.
Hey, Brian,
Rumpus, there's no way to measure rotation.
Brian, drop and
Yeah,
rejoin.
okay.
It's bad.
Okay, will do.
So I think there are about 10 easy proofs of rotation. I mean, I've given you 4 of
10
them.
easy assertions of your globe model and effects that you have tied to it that can't be shown experimentally. Yeah.
Experiments. Yeah, they've been proved experimentally. So if you want to deny science, then you can. That's what you do. But we have 10 proofs.
Did you say experimentally?
Experimentally, yes.
Show us one proof experimentally that the
I
Earth
just
turns.
told you about one. My God, do you not listen? 1, the gyroscope orientation of 15 degrees per hour. 2, I just described the bat dropping things vertically and they're being
The
deviated.
gyroscope, how did you vary the rotation of the Earth?
You don't have to vary. You can see that you've got a 15-degree change in position.
Rumpus. Come
Oh
on,
my
you're not
God.
an amateur, Rumpus.
Come on, just try this again. Gyroscopes maintain their orientation in space. So if you get a degree change in their orientation over an hour of 15 degrees, you know that that's being rotated. It's very simple.
Yes, gyroscopes maintain rigidity in space. I've seen both experiments. I've seen both tests, and
over a period of an hour, it changed by 15 degrees, and you know the gyroscope is still pointing in the same direction. Yet the thing around it has moved. It's changed its orientation with respect to its container. You then know that the container's rotated. This is really simple.
only in your brain, Rumpus. Only in your brain.
It's too complicated for you, I understand that. But to anybody with the tiniest bit of IQ and above average would be able to say what I just described is an absolute proof of rotation.
You have a massive
we just proved
superiority
you're wrong with
complex,
the Coriolis
Rumpus.
here, Rumpus. I mean,
Let me interrupt here for just a second. Hold on, I got to do some show business. Gadfly 13, 5 British pounds. I thought I already read this one, but I must have missed it. The only answer Rumpus blurts out is you don't understand any of my assumptions. Maybe I was muted at that time when I screwed up my mic. Sorry about that, guys. And Esteban Ilabaca, anyone care to explain why Coriolis effect is considered in mech engineering and design FR rotating machinery? It generates vibration that can be critical, CLP 2,500 pounds. Let me take a crack at answering Esteban. I don't think anybody is denying that there's Coriolis effect per se. What we're talking about is Earth-based Coriolis. So is he saying that Earth-based Coriolis is designed into these machines, or I'd have to have more information in order to even address that. But if anybody knows more about that subject, go ahead and take a crack at it.
Oh, another proof, of course, is that things weigh differently at different latitudes, which can only happen on a rotating Earth.
Which you also tie to a rotating Earth without experimental evidence. Assumptions.
What do you mean assumptions?
Rumpus, can I ask you a question?
Just in denial. Hold on, let me just. Some idiot made some assumption. We can get. You're just denying all these observations.
If you call us science denialer one more time, I'm going to kick you. Just stop. Effie Evangelist, go ahead.
Just stop.
Measure these things.
Rumpus,
Rumpus,
can you just shush?
Denying it that we've done this measurement.
Just for a sec.
Go ahead.
Or you could just keep talking incessantly. That's another thing you could do. Now, correct me if I'm wrong. Did you say
he just went on deaf. Look at what.
No, I
coward
muted him
did.
so that Effie Evangelist could
Yeah,
talk.
but that's what he does. He goes on deaf. He's not going to hear a word you say now.
Oh, okay, that's fine.
There's no
Yeah,
point
well,
in
it's
even
going to be hard.
addressing them.
Can someone elaborate for me? Did he say that if we dropped a bowling ball off the Eiffel Tower, it would exhibit Coriolis and it would not travel straight down? Is that what he said?
Correct. Yes.
They have
so
to
the
say
question
that.
I was going to ask him is, okay, on the basis of that, would you be prepared to stand directly below me at the top of the Eiffel Tower, and I've got 100 bowling balls, and I can just drop them one after another straight down,
I would
and they
pay,
will
brother.
kill you.
I would
They
pay
will.
for front row.
They will kill. They definitely will kill you if they hit you. Would you stand there because you're that confident in Coriolis? That's my question.
Of course, you didn't hear a word of it.
I'm interested in how the Earth spins differently depending on how fast the object's going. That's interesting. I mean, that's essentially what he's saying. He's saying the Coriolis affects them differently depending on how fast they're traveling. So something's going to deviate more if it's going faster, less if it's going slower. I don't know. It sounds crazy.
Silent Zero came in with a $5 super chat with a good point. Did he just say that science proves Earth spin? I thought science didn't prove
I
that.
challenged him on any. Yep.
Did he really say that just now? This is
Yeah.
why they don't fuck. This is why they don't fuck with him in gems, bro. I'm telling you.
Pete Bremble says Rumpus is a legend.
In his own mind.
Yeah.
Maybe Pete owns the circus that Rumpus is a clown in.
Yeah, it's not always a good thing to be a legend.
Yeah.
All right, guys, we got about 7 minutes until 8 o'clock. I am cutting this streams at 3 hours most nights. But let's go do final thoughts and get the heck out of here. All right. Rumpus is on deaf and in mute, so we'll skip him. Brian, you there still?
Yeah, man, I'm here. The stream, unfortunately, but man, I wish I could have had a go at Rumpus on his Coriolis because I could have made him double
Oh, he did a lot of dope speaking.
like silly, but that's okay. Y'all did good enough. Yeah, exactly. But I'm gonna say,
sorry.
yeah, I'm gonna pass it on, man. I'm gonna listen back to it and appreciate everything, Brandon. Thank you, man.
Yep, thanks, Brian. Yeah, there's some bad echo coming from your side, just so you know. Before we go to Crow XE, we got a super chat from Titanic Terrarium for 5 SGD. Not familiar with what that is. Why is it impossible to make a flat Earth map that comports with directly observable reality? I don't know how someone could say it's impossible. That's a pretty bold statement. But I don't think it's impossible. It just hasn't been done that I know of yet. All right, Crow XE.
Yeah, hello, can you hear me?
Yep, we can hear you.
Yeah, so just my final thoughts is if anyone can do the experiments that I suggested in your backyard, use a compass, look at a target, move sideways, exactly sideways, certain amount of distance, measure the angle of that target, find the difference, degrees, put it in that site, converts, or whatever, and you get it. And the other thing, there was a game I used to play, 3 houses and electricity, sewage, and water. Do you know this game, Brandon?
Sim City.
I don't know the name, but it looks like
Sim City.
some people. Yeah, and try to connect without them crossing each other. So here's the game that I suggest. Try to draw a surface and certain points with equal angles to any object away from the surface, and show that the angles can be observed. Like the change in the angle is consistent with the distance. That's it. Thank you.
Okay, thanks, Crow. Effie Evangelist?
Yeah, the more we listen to these guys, for me, the more just evident it is that everything they talk about is a reverse engineering back from the story that they want to tell. I'm actually going to go and do an exercise, and I'm going to find some different numbers that'll make Polaris work at the so-called 45th parallel or whatever it is, 45-degree line. They don't measure anything. They calculate everything and call it measurement. There's double speak. It's to people that just aren't in this every day. It makes perfect sense. We all know, but as soon as you drill down and ask them real questions and prove this and how do you measure, it all comes back to lines on a piece of paper, protractors, and none of it actually comports to the real world. So that's my bit. Thanks. Good show, Brandon.
Yeah, I share much of those
Just
same
final
sentiments. Gleam? Yeah, his final thoughts, yep. Gleam, go ahead.
Brilliant show. Nice one, Brandon. Salute Ranty if he's still in the chat. I'm sure he is. And Effie Evangelist, I've just posted up the maths for Polaris every single degree. It's just, again, another reverse engineer or coordinate transform of the globe to a flat Earth.
Excellent, Glenn. Thanks, mate. I'll have a look at it.
Yeah, and all I can say is, I don't know what it is. Rumpus should have clear and concise answers, but he just wanders off. We end up getting a book with him, a whole storybook. And I know that he wants to explain himself in as much as he wants to give all the information, but sometimes it just goes everything other than the information that you're asking him to give. Yeah, so it's just avoidance tactics is what I'm saying. Salute and good evening. Take care.
Awesome, Gleam. Thanks. Jeremy.
Yeah, I just want to say fuck the rumpus. We were talking about the Coriolis effect and the deviation and where the bullets land in the same spot, and then he said later he was talking about Coriolis for. It's just a bunch of bullshit with these guys, man. Yeah, like what the last guy said, you get a 5-minute every time you ask him something, you get a 5-minute response from a yes or no question. It's ridiculous. I want to know how the speed of the object matters. Makes the Earth rotate differently underneath it over the same distance. Like it's crazy what he says. Anyways, that's all. Have a good night.
Yep. Thanks, Jeremy. Rakia.
Yeah, I think we're making progress. Good show. I don't like the rumpus. I mean, it's like driving down a dead end street. You get down there, go in reverse, and then drive forward again to the dead end sign. So, waste of time and energy in my book. Thanks.
Yep. Thanks, Rakia. SE.
Hey, Brandon. Thanks a lot, bro. Another great show. Just showing again how delusional rumpus is. The Coriolis vision, it's just that. It's a visual effect. Yes, it's a real effect, but we don't see it on Earth. We can easily demonstrate it on a merry-go-round. So rumpus, you're delusional. The Coriolis vision cannot affect anything. Peace out, guys.
Cool. Thanks, Essie. And Bob.
Yeah, I think that people that were listening in and stuff, if they're thinking about it logically, they'll see that there's been a number of issues with Crow and Rumpus and the way that they're stating things and going back and either changing things or not lining up their statements properly. And yeah, go ahead and do Crow's little experiment in your backyard, and then if you want to verify that his calculation worked properly and check to see for sure if those are the right measurements, go ahead and measure it to verify those findings, like anyone would normally do if they wanted to verify their calculation. They would measure the thing.
Yep. Well said. Right the hand. Thanks, Bob.
Yeah, well, good show, Brandon. Thanks for keeping it going. And I just wanted to say, like, when they say, oh, Mars is X distance away, it's moving at X speed, right? You can change all of that, right? Like with just different calculations, you can put Mars further away, moving slower or closer, and you can get any number. I think there might be an infinite number of possibilities on how far everything away can be and still move, and it still works, right? Like just make it bigger and move slower, or make it closer and faster. It's numbers. It's just numbers making them fit. So there can't be just one, especially when you're making up how far away and how fast they are going. You can make it work no matter what. Just make it go faster.
Yep, well said. Thanks, right hand. Yep, my final thoughts. Good show. Appreciate everybody coming, supporting the show. Thought it was good stuff. I share much of the same sentiments you do. Just feels like we're chasing our tails sometimes and not getting anywhere. But I thought we did have some good discussions tonight, so I appreciate that. Appreciate everybody showing up. Same place tomorrow, same time. We'll see y'all there. I do have one super chat to read right here at the very end. Titanic Terrarium again. Thanks, Titanic Terrarium. If you take 4 points on the Earth and 4 known flight times, and there is no way to make these match on a flat surface, it's impossible. So maybe we'll have to discuss that next time. Sorry it was so late in the show, Titanic Terrarium, but thanks for your super chat. All right, guys, I'm going to shut it down. Have a good night.